Look up at the night sky, and you see a familiar scene. One sun has set, leaving a single, distant moon and a scattering of stars. It's a universe of singularities, of lonely suns with their families of planets. But what if everything you thought was normal was just a cosmic coincidence? What if our solitary sun is the exception, not the rule? We are about to venture into a reality so bizarre, it challenges the very foundation of what we know. Picture a cosmic ballet not with one star but with seven. A septuple star system is not just a cluster of suns, it is a gravitational masterpiece, a chaotic and beautiful symphony of seven massive bodies bound together in an intricate, perpetual dance. The sheer complexity of such a system is almost beyond human comprehension, a place where multiple suns would rise and set in a sky filled with light and shadow, where the concept of a simple day and night is thrown into a blender of celestial madness. The discoveries emerging from the study of these septuple star systems are rewriting the textbooks of astronomy. Scientists are uncovering truths that sound more like science fiction than hard data. We are talking about gravitational forces so extreme they warp space and time, orbits so chaotic they defy prediction, and environments so strange they might just harbor forms of life we cannot even imagine. For decades, we assumed that complex life needed the steady, predictable warmth of a single star. But what if life, in its relentless creativity, could find a way in the flickering, multi-sunlit chaos of a system with seven stars? The possibilities are as thrilling as they are profound, suggesting that the universe's capacity for wonder is infinitely greater than we ever dared to dream. This video is your passport to the frontier of this incredible science. We have gathered 50 of the most astonishing, mind-bending discoveries about these gravitational marvels. Each one is a piece of a puzzle that is slowly revealing a universe far more dynamic, strange, and magnificent than we ever anticipated. From the way these stars are born in tumultuous nurseries to the potential for exotic worlds orbiting within their complex gravitational webs, we are about to embark on a journey that will completely reshape your perspective. So prepare to have your curiosity ignited and your sense of wonder expanded as we dive deep into the 50 strangest discoveries about septuple star systems. Our journey into this bizarre celestial realm begins with the very first system that proved such a staggering arrangement was even possible. For a long time, the idea of a septuple star system was purely theoretical, a mathematical curiosity that most astronomers thought would be too unstable to exist for long. That all changed with the intense scrutiny of a star we now know as Cassiopeiae. Nestled within the familiar W-shaped constellation of Cassiopeiae, this point of light appeared to early telescopes to be just another bright star. But something was off. Its light seemed to waver in strange, complex rhythms that a simple binary pair couldn't explain. Unraveling this cosmic mystery became a decades-long puzzle, pushing observational technology to its absolute limits. The key to solving it lay in two sophisticated techniques. The first, called radial velocity, measures the subtle wobble of a star as it's gently tugged by the gravity of an unseen companion. As a star moves towards us, its light shifts slightly to the blue end of the spectrum. As it moves away, it shifts to red. For Cassiopeiae, these wobbles weren't simple back and forths. They were a chaotic mess of overlapping signals, like trying to pick out individual instruments in a symphony playing 7 different tunes at once. The second technique, astrometry, precisely maps the tiny changes in a star's position on the sky. Even the most minute dance steps caused by the gravitational pull of multiple partners could be detected. It was the combination of these methods that finally allowed astronomers to isolate not 2, not 3, but 7 distinct stellar signatures. What emerged was a picture of incredible order within the apparent chaos. A septuple system doesn't mean 7 stars all chaotically buzzing around a single point. Instead, Cassiopeiae is organized in a stunning hierarchical structure, a gravitational family tree. Imagine it like a cosmic dance on multiple levels. At the most intimate level, you have pairs of stars locked in a tight, rapid orbit. These are the binary couples. These pairs themselves then orbit each other, forming a stable quartet. This larger group engages in a stately, slow dance with another pair of stars, and the entire complex assembly of 6 stars is then gravitationally bound to a 7th, more distant stellar companion. It's a system within a system within a system, a Russian nesting doll written in gravity and starlight. This hierarchical arrangement is the secret to its longevity, providing the stability needed for such a complex family to survive for billions of years. The sheer existence of such a complex system immediately raises a profound question. How does it not simply fly apart? The gravitational forces between 7 massive objects should, in theory, lead to a spectacularly short-lived cosmic disaster. The secret, as astronomers discovered, lies in the extreme hierarchical orbits that define systems like Cassiopeiae. This isn't a free-for-all mosh pit of stars. It's a meticulously organized celestial bureaucracy with strict rules governing who interacts with whom. To understand this, we need to picture the system not as a single entity, but as a series of distinct gravitational neighborhoods. Think of it as a nested set of spinning tops, each spinning at a different speed and scale. At the very core, you have the tightest, fastest-moving pair of stars. These two are so close together that their gravitational bond is incredibly strong, and they whirl around a shared center of gravity in a matter of days or even hours. This is the innermost top, spinning furiously. Now, imagine that this entire spinning duo is itself part of a slightly larger top. It orbits another pair of stars, but this dance happens at a much greater distance and over a much longer period, perhaps taking years to complete a single loop. The gravitational pull between these two pairs is significant, but it's far weaker than the forces binding each individual pair together. This creates a stable quartet, a system within a system. This pattern repeats itself on an even grander scale. This quartet of stars then engages in a slow, stately orbit with another binary pair. The distances involved here are vast, and the orbital period could stretch to centuries. The gravitational tugs at this level are gentle, like a faint whisper compared to the shouting matches happening within the inner binaries. Finally, the entire assembly of 6 stars is gravitationally tied to a 7th, lone stellar companion that orbits the entire central cluster from an immense distance, a journey that might take thousands of years. The stability comes from this hierarchy of scales. The stars in the tight inner binaries are so preoccupied with their immediate partners that they are largely oblivious to the gentler gravitational nudges from the more distant stars. It's this separation of influence that prevents the chaotic interactions that would otherwise lead to stars being flung out into the void. This gravitational choreography is what allows septuple systems to persist for billions of years. It's a delicate balance, but one that is surprisingly robust. The system essentially manages its own energy, keeping the most violent interactions localized and contained. Without this hierarchical structure, the gravitational potential energy would be redistributed chaotically, inevitably ejecting stars until only a simpler, stable system remained. It's a cosmic dance of precision where every star knows its place and its partners, ensuring the ballet continues uninterrupted across eons. Given the intricate gravitational choreography required for stability, it's no surprise that discovering a septuple star system feels like winning the cosmic lottery. The sheer improbability of such a configuration is staggering. Astronomers have catalogued countless star systems, and the vast majority are solitary like our own Sun. When we move into the realm of multiple stars, the numbers drop off dramatically. Binary systems with 2 stars are incredibly common, making up nearly half of all Sun-like stars in our galaxy. Triple star systems are far less frequent, but we know of many, like the famous Alpha Centauri system, which contains 3 stars. Quadruple systems become a genuine rarity, and quintuple systems are exotic oddities with only a few dozen confirmed examples. But when we push the count to 7, the number of confirmed, stable septuple systems can be counted on one hand. This extreme scarcity highlights a fundamental truth about star formation. Building a system with 7 gravitationally bound members requires a perfect storm of conditions within a stellar nursery that is both incredibly dense and exceptionally calm. Imagine a vast cloud of gas and dust collapsing under its own gravity. As it fragments, multiple dense cores begin to form, each destined to become a star. In a typical region, these protostars would be scattered, forming separate single or binary systems. But in the specific environment needed for a septuple, the cloud must fragment into several cores that remain extremely close together, all while having just the right amount of rotational energy and not too much turbulent motion. If the cloud is too turbulent, the nascent stars are kicked away from each other before they can establish stable bonds. If it's too calm and lacks rotation, the entire cloud might simply collapse into 1 or 2 massive stars without fragmenting sufficiently. The sweet spot is a narrow band of physical parameters where multiple fragments form in close proximity, and their initial velocities are just right to allow them to pair off into binaries, which then gently capture each other in a hierarchical dance. It's a delicate process that can easily be disrupted by a passing shockwave from a nearby supernova or the gravitational influence of another star cluster. This is why these systems are not just rare, they are statistical miracles, offering us a unique window into the most extreme outcomes of the star formation process. This gravitational stability, however, is only the calm before the storm. The true cosmic drama in a septuple system unfolds over billions of years as the stars themselves begin to age and change. While the orbital hierarchy provides a stable framework, it does nothing to protect the stars from their own internal evolution. Each star lives its life at a different pace depending on its mass. The most massive stars burn through their nuclear fuel in a cosmic frenzy, living fast and dying young, while their lighter siblings simmer slowly for eons. It is this disparity that sets the stage for one of the most chaotic and spectacular phenomena astronomers have discovered: unstable mass transfer. In a simpler binary system, when a star swells into a red giant, it can tidally transfer material onto its companion if they are close enough. This process is complex but somewhat predictable. Now amplify that scenario by a factor of 7. In the dense inner core of a septuple system, a single evolving star isn't just interacting with one neighbor, it's at the gravitational center of a web of potential partners. When a star in one of the tight inner binaries exhausts the hydrogen in its core, it begins to balloon outward, its outer layers becoming tenuous and loosely bound by gravity. In this inflated state, it can easily fill its Roche lobe, the region of space where its material is gravitationally dominated by itself. Once it crosses this boundary, its stellar substance begins to flow toward the most powerful gravitational well nearby, which is usually its immediate binary companion. But here's where the septuple chaos begins. That stream of gas doesn't just travel in a clean, simple arc. The gravitational pulls from the other nearby stars in the system, the other binary pair orbiting closely, for instance, tug and distort this stream of matter. It's like trying to pour water from one jug to another while riding a violently shaking carousel. The flow of material can become unstable, forming a complex disk around the receiving star that is itself warped and perturbed by external forces. In some scenarios, the material might not even settle onto one star cleanly. It could be gravitationally snatched by another passing member of the stellar group, or it could form a temporary common envelope, a shroud of gas that envelops not just 2, but potentially 3 stars, causing drastic friction and orbital decay. This unstable transfer of mass has dramatic consequences. One of the most explosive is the triggering of nova eruptions. If the star receiving the material is a white dwarf, the hot, dense corpse of a star like our Sun, the fresh hydrogen piling up on its surface can ignite in a runaway thermonuclear explosion. This nova blast can shine with the intensity of hundreds of thousands of suns, and in a septuple system, such an eruption would bathe all the other stars in a sudden, intense wave of radiation and high-energy particles. But because the mass transfer is so messy and unpredictable, these nova could occur with strange irregularity or even in chains as material from one event triggers instability in another part of the system. Perhaps even stranger is the creation of what astronomers call blue stragglers. These are stars that appear mysteriously young and blue, shining brightly long after all their stellar siblings of similar mass should have aged and died. In the frantic environment of a septuple system, they are born from stellar cannibalism. The unstable mass transfer can lead to two lower mass stars actually colliding and merging, creating a single, rejuvenated star with a fresh supply of hydrogen fuel for its core. This new, more massive star then burns hotter and bluer than its neighbors, standing out as a stellar anomaly. In a system with 7 stars, the opportunities for such chaotic mergers are vastly increased, potentially creating multiple generations of blue stragglers over the system's lifetime, each one a testament to a violent, transformative event in the system's history. And this chaotic stellar evolution leads us to one of the most captivating questions of all. Could planets even exist in such a tumultuous environment? The concept of a Polarissima emerges from this very speculation, a hypothetical world orbiting within a septuple star system. The name itself evokes an ultimate extreme, a planet where the sky is not dominated by one sun, but is instead a canvas for multiple, each tracing its own path through the heavens. The idea of such a world captures the imagination, but the path to its formation is riddled with cosmic obstacles. The first and greatest challenge is the violence of the system's youth. Planets are born from the vast, swirling disks of gas and dust that surround newborn stars. In a serene system like our own, this protoplanetary disk was a relatively calm nursery, allowing dust grains to gently clump together, eventually building up into planets over millions of years. But in the core of a septuple system, the environment is anything but calm. The fierce gravitational tides from multiple, closely orbiting stars would constantly stir and disrupt these nascent disks. A young planetesimal trying to form would be subjected to relentless gravitational kicks, like a child trying to build a sandcastle in the midst of a hurricane. The powerful stellar winds and intense radiation from several massive hot stars would also blow away the light gas and dust needed for planet formation, potentially stripping the disk bare before any substantial worlds could ever coalesce. For a long time, astronomers believed this meant the inner regions of such complex systems would be planetary deserts. Yet, nature often finds a way in the quiet margins. While the system's heart may be a chaotic maelstrom, its outer reaches tell a different story. Far beyond the intricate dance of the inner binaries and quadruples, in the domain of the seventh, most distant stellar companion, a strange stability can be found. At such immense distances, the gravitational pull of the central stellar cluster simplifies. Instead of feeling the individual tugs of 6 separate stars, a planet would essentially orbit the collective center of mass of the entire group, as if it were a single, massive object. In this vast orbital space, a protoplanetary disk could survive relatively undisturbed, allowing a Polarissima to form in a stable, albeit utterly unique, environment. The sky from the surface of such a world would be a spectacle beyond anything we can experience on Earth. There would be no single defining sunrise or sunset. Instead, the suns would rise and set at different times, creating a day with a rhythm of shifting light and complex shadows. For long periods, multiple suns could be above the horizon simultaneously, casting several distinct shadows from every object. The light itself would be a blend of different colors and intensities depending on the types of stars present. Imagine the warm, yellow light of a sun-like star mixing with the harsh, blue-white glare of a more massive, hotter star. There would be times of near-perpetual daylight when at least one star is always in the sky, and other times of profound, multi-star twilight with the sky glowing in eerie, layered hues as each sun dips below the horizon in succession. The concept of night might be a rare event occurring only when all 7 stars are aligned on the opposite side of the planet, offering a brief, truly dark window to view the alien galaxy beyond. The seasons on a Polarissima would be equally mind-bending. They wouldn't be driven by a simple axial tilt relative to one star, but by the complex, changing positions of all the stars in the system over their long orbital periods. A summer might occur when the planet is closest to the brightest stellar member in its orbit, while a winter could coincide with a configuration where the planet is farther from the main cluster and the dominant light sources are the dimmer, redder stars. These seasonal cycles would be incredibly long and complex, potentially lasting for centuries or even millennia, creating climate patterns that are utterly alien and unpredictable. The very possibility of a Polarissima challenges our Earth-centric view of habitability, suggesting that even in the most extreme gravitational environments, pockets of stability can arise, hosting worlds with skies of unimaginable beauty and complexity. But the strangeness doesn't end with the potential for alien worlds. It's woven into the very fabric of the stars themselves. One of the most baffling discoveries about these systems is that the stars within them are not always a uniform family. In a typical star cluster, all the members are born from the same giant cloud of gas and dust at roughly the same time, like siblings from a single parent. They share a common age and a similar chemical makeup. Yet, when astronomers turn their spectroscopes toward a septuple system, they sometimes find a bewildering mix of stellar generations. It's as if you walked into a family reunion and found newborns, teenagers, middle-aged adults, and elderly grandparents, all claiming to be direct brothers and sisters. This finding sends shockwaves through our understanding of how stars are born. The primary tool for uncovering this anomaly is spectroscopy, which acts like a cosmic DNA test for stars. By breaking a star's light into a rainbow spectrum, scientists can identify the unique fingerprints of elements present in its atmosphere. They can also estimate its age based on its temperature, luminosity, and spin rate. In several septuple systems, this analysis reveals stark differences. One star might be a youthful, hot blue giant, blazing with energy and rich in specific metals forged in recent supernova. Orbiting right alongside it could be a much older, cooler, red dwarf that is chemically primitive, containing only the basic elements from the early universe. This disparity is a major puzzle. If they all formed together from the same primordial cloud, they should have the same chemical recipe. The presence of such different stellar populations points to a far more dramatic and violent history. This forces astronomers to consider 2 radical possibilities. The first is that the system's formation was incredibly turbulent and protracted. Instead of a single, smooth collapse of a gas cloud, the nursery that gave birth to the septuple may have experienced multiple waves of star formation over millions of years. Perhaps an initial group of stars formed, and then a shock wave from a nearby event, like a supernova, compressed a remaining pocket of gas, triggering a second, later burst of star birth within the same gravitational well. This would create stars of different ages bound together from the very beginning. The second, even more thrilling possibility is stellar capture. Imagine the septuple system in its youth, perhaps starting as a quintet or a sextet, sailing through a dense star-forming region. Its complex gravity could act like a net, snagging a lone, wandering star that happened to pass too close. this captured star would be an interstellar orphan with its own distinct age and chemical history, suddenly adopted into a new chaotic family. The hierarchical structure of these systems makes this scenario surprisingly plausible. The seventh, most distant star in many of these systems is often the one with the anomalous properties, suggesting it might be the captured outsider, now locked into a wide, billion-year orbit around the inner core of original members. This idea transforms our view of these systems from closed, insular families into dynamic hubs that can acquire new members through gravitational theft, creating the peculiar stellar mosaics we observe today. This stellar chaos, with its captured stars and violent mergers, is merely the prelude to the single most disruptive event that can occur within a septuple system: the death of a star. When the most massive member of this cosmic family reaches the end of its life, it doesn't fade away quietly. It goes out in the most spectacular fashion imaginable, a supernova. And in the densely packed, gravitationally interwoven environment of a septuple system, a supernova is not just a brilliant flash. It is a fundamental reset button, a cataclysm that can rewrite the system's entire destiny in an instant. The drama begins deep within the core of a massive star, perhaps 10 or 20 times heavier than our Sun. For millions of years, it has been fusing elements in a desperate battle against gravity, building up a core of iron. But iron is a cosmic dead end. It cannot be fused to release energy. When the iron core grows too large, gravity wins in a fraction of a second. The core collapses from the size of a planet down to a city-sized ball of neutrons, and the outer layers of the star, with nothing left to support them, come crashing down at a quarter of the speed of light, only to rebound off the impossibly dense new core in a titanic shockwave. This is the supernova explosion, shining brighter than an entire galaxy. But for the surviving stars in the system, the light show is the least of their concerns. The real impact comes from two terrifying consequences: the sudden loss of mass and the powerful neutron star kick. First, consider the mass. In that colossal explosion, the star instantly sheds over 80% of its substance, blasting it out into space. In any gravitational system, stability is a delicate balance dictated by mass. Imagine 6 dancers holding hands, spinning around a seventh who is the heaviest central anchor. Now imagine that central dancer suddenly vanishes, leaving behind only a fraction of their weight. The entire choreography falls into disarray. The same happens in the star system. The gravitational glue that held the intricate orbits together is drastically weakened. Orbits that were once stable become wildly eccentric or simply unravel. The sudden change can cause the remaining stars to fly apart, their mutual gravitational attraction no longer strong enough to hold the family together. But the mass loss is only half the story. The newly born neutron star at the heart of the explosion often receives a tremendous kick. Due to asymmetries in the collapse, this city-sized ball of ultra-dense matter can be shot out like a bullet from a gun, reaching speeds of hundreds of kilometers per second. This is not a gentle nudge, it's a violent recoil that violently shoves the entire system. Because the neutron star was, until moments before, an integral part of the gravitational balance, its explosive ejection imparts a momentum to the rest of the system. The result is like a grenade exploding in the middle of a carefully arranged house of cards. The entire septuple system can be sent careening through the galaxy as a runaway group, a cluster of stars flung from its birthplace. Alternatively, the kick might be just enough to destabilize the delicate hierarchical dance, causing 2 of the inner binary pairs to fall into a closer, more dangerous orbit, potentially leading to a future collision, or flinging one or more of the stars out on a one-way trip into the interstellar void forever alone. The aftermath of such an event leaves behind a profoundly changed system. What was once a stable septuple might now be a sextuple or even a quintuple. The system's trajectory through the galaxy would be altered, and the remaining stars would be left in new, often more chaotic, orbits. The supernova would have also enriched the system with heavy elements, seeding the remaining protoplanetary disks around the other stars with the building blocks of planets and potentially life. It's a paradoxical event of both destruction and creation. The death of one star introduces chaos, but it also sows the seeds for new worlds, all while demonstrating the incredible power of stellar evolution to reshape the cosmos on the grandest of scales. For astronomers trying to decipher the secrets of these systems, the most direct clues come not from images, which often show just a single point of light, but from the subtle, rhythmic changes in their brightness over time. This record of light, known as a light curve, is like the system's electrocardiogram, a heartbeat tracing that reveals the complex motions within. In a simple eclipsing binary system, the light curve is beautifully predictable, a steady brightness, then a smooth dip as one star passes in front of the other, followed by a return to normal. It's a clean, repeating sine wave, but when you point a telescope at a septuple star system, the resulting light curve is anything but simple. It's a chaotic, jagged, and perpetually surprising graph that looks more like the readout of a seismic event than a stellar dance. The overlapping orbits of 7 stars create a constant and unpredictable series of eclipses, transits, and mutual brightening, generating patterns so complex they have pushed the limits of our computational power to model. The strangeness emerges from the sheer improbability of alignment. With so many stars orbiting on different planes and periods, partial eclipses are the norm. Imagine 2 stars, one large and dim, the other small and brilliant, passing in front of each other from our vantage point. The resulting dip in light isn't a clean, symmetrical curve. It's a lopsided, multi-tiered step down in brightness. Now layer on a 3rd star eclipsing one of the first 2 while that initial eclipse is still underway. The light curve becomes a tangled mess of overlapping signals. Astronomers have observed light curves where the brightness flickers erratically for weeks, with mini dips nested inside larger declines, creating a pattern that never repeats exactly. This is the hallmark of a septuple system, a light curve that is essentially non-periodic over human timescales, a fingerprint of gravitational complexity that is unique in the galaxy. Beyond these expected, albeit chaotic, eclipses, observers have recorded dimming events that defy all conventional explanation. These aren't the sharp, predictable transits of a star. They are slow, gradual, and asymmetrical fadings that can last for months or even years, sometimes reducing the system's light by a significant percentage before mysteriously returning to normal. One leading theory points to vast, warped clouds of dust. In the turbulent gravitational environment of the inner system, the unstable mass transfer between stars can lead to the creation of colossal circumstellar disks, not the orderly, flat rings we see around young stars, but puffed up, wobbly structures of gas and fine dust. As these titanic, misshapen disks orbit, they can drift in front of our line of sight, casting a deep and variable shadow that dims the combined light of several stars at once. The irregular shape of the disk would account for the slow, uneven nature of the dimming, a celestial cloud passing overhead on a scale almost too large to comprehend. An even more exotic possibility involves the aftermath of those stellar collisions and violent mass transfers. When 2 stars merge or engage in a destructive dance, they can blast an enormous amount of debris into space. This debris, ranging from tiny dust grains to asteroid-sized fragments, doesn't simply disperse. Instead, it can clump together under its own gravity, forming a complex, evolving swarm of material on a wide orbit. As this swarm passes between us and the stellar core, it would cause a gradual, speckled dimming. Because the swarm is not a solid object but a loose collection of countless fragments, the resulting light curve would be a stuttering, unpredictable decline, full of tiny bumps and dips as individual dust clouds or planetesimals within the swarm block the light. These mysterious events suggest that the septuple system is not just a collection of stars, but a dynamic factory for creating strange and transient structures of cosmic debris, offering us a fleeting glimpse into the most violent and creative processes of stellar evolution. All this talk of eclipses and light curves highlights a fundamental truth about studying these systems. We are almost always interpreting shadows on a cave wall. We deduce the existence of 7 stars from their gravitational tugs and their intricate dances in front of each other, but what about actually seeing them? The ultimate goal for any astronomer is direct imaging to point a telescope and resolve those 7 points of light as distinct individuals. Yet, this discovery reveals that even with our most advanced technology, capturing a family portrait of a septuple star system remains one of the most formidable challenges in all of observational astronomy. The primary obstacle is a matter of simple geometry and staggering distance. Even the closest known septuple systems are many hundreds of light years away. From our vantage point, the angular separation between the stars, the apparent distance between them in our sky, is infinitesimally small. To put it in perspective, the tightest inner binaries in a system like Cassiopeiae might be separated by a distance similar to that between the Sun and Saturn. But viewed from hundreds of light years away, that vast distance subtends an angle smaller than the width of a human hair held at arm's length. For even the most powerful single-mirror telescopes like the Hubble or the James Webb Space Telescope, this is far beyond their native resolution. They would see the entire system as a single, blurry blob of light, its secrets completely merged into one indistinguishable point. To overcome this, astronomers turn to a brilliant and complex technique known as interferometry. This method doesn't rely on building one impossibly large mirror. Instead, it combines the light from multiple, smaller telescopes separated by a great distance, effectively creating a virtual telescope as wide as the distance between them. It's like giving a single eye the compound vision of a fly. By precisely measuring how the light waves from the target interfere with each other as they arrive at the different telescopes, supercomputers can reconstruct an image with a resolution that would be impossible for any single instrument. Using facilities like the Very Large Telescope Interferometer in Chile or the Chara Array in California, scientists have managed to just barely, resolve the brightest components of these systems. The resulting images are not the stunning, detailed portraits we're used to seeing of nebulas or galaxies. They are often just a few pixels of data, but those pixels represent a monumental achievement. They confirm that the light comes not from one location, but from 2 or 3 distinct points. This allows astronomers to directly measure the separation between the closest pairs, providing crucial ground truth data to validate the orbital models built from spectroscopy and light curves. However, resolving all 7 stars individually remains a pipe dream for now. The fainter, more distant companions are simply lost in the glare of their brighter siblings. The hierarchical structure that grants the system its stability also works against us here, as the dimmest members are often too close to the brightest ones in angular terms for even interferometry to tease apart. For the foreseeable future, the complete septuple system will remain a beautiful phantom, known by its effects but forever eluding a perfect portrait. All that gravitational complexity doesn't just dictate the stars' paths, it actively reshapes their very bodies. We often picture stars as perfect, serene spheres of incandescent gas, but in the crowded neighborhoods of a septuple system, that ideal form is a luxury they cannot afford. The relentless, changing gravitational pulls from multiple close companions exert tidal forces of immense power, stretching and squeezing these colossal balls of plasma into distorted shapes. It's a process similar to how our moon's gravity gently tugs on Earth's oceans, creating the tides. Now amplify that effect by a factor of millions. Instead of a gentle pull on water, imagine a force so strong it can deform a star millions of kilometers in diameter. This leads to a phenomenon far more extreme than simple deformation: complete tidal locking. In our solar system, we see a mild version of this with our moon, which rotates on its axis at the same rate it orbits Earth, ensuring we only ever see one side of it. In a septuple system, this principle is taken to its absolute limit. The stars in the tightest inner binaries are the most susceptible. The gravitational pull between them is so overpowering that it acts as a cosmic brake, swiftly slowing their individual spins until each star's rotation becomes perfectly synchronized with its orbit around its partner. The result is a permanent celestial embrace where each star presents the same face to the other for all eternity. They are locked in a gravitational stalemate, one hemisphere perpetually bathed in the intense light of its companion, while the other stares out into the eternal cold of the surrounding system. The consequences of this locking are profound. The star facing its partner becomes a dayside of unimaginable heat. It is continuously bombarded by the radiation from its nearby stellar neighbor, superheating its atmosphere. This can create a permanent, raging hotspot, altering the star's internal circulation and even its nuclear fusion processes. Meanwhile, the far side, the eternal night side, cools dramatically. This drastic temperature difference between the two hemispheres can drive ferocious winds, as atmosphere screams from the hot side to the cold side in a perpetual global hurricane. The star is no longer a uniform sphere. It becomes a lopsided, egg-shaped object with its long axis perpetually pointed toward its gravitational master. This distortion is not just superficial. It affects the star's density, its magnetic field dynamics, and ultimately, its long-term evolution, creating a stellar environment that is utterly alien compared to anything we see in our own solitary solar system. This gravitational distortion is just one way a septuple system leaves its mark on its members, but the system's influence doesn't stop at its own borders. The same intricate dance of forces that lock stars together can also, paradoxically, be the engine that violently expels them. We've observed solitary stars streaking across the galaxy at millions of miles per hour, moving so fast they are destined to escape the Milky Way's gravitational pull entirely. For a long time, the origin of these hypervelocity stars was a mystery, often attributed to close encounters with the supermassive black hole at the galactic center. However, recent simulations point to a startling new possibility. Septuple star systems may be unexpected factories for these interstellar cannonballs. The mechanism is a gravitational slingshot of breathtaking precision, known as a three-body interaction. Within the crowded core of a septuple system, especially during a close orbital pass, it's not uncommon for three stars to find themselves in a temporarily unstable configuration. Imagine three dancers, two locked in a tight, fast spin, while a third swings in on a wider path. As the third star approaches, the gravitational dynamics shift from a stable pair plus one to a chaotic, three-way tug of war. For a brief moment, their motions become a complex calculation of pulls and pushes, a gravitational ballet where energy is traded between them at an incredible rate. In most cases, this interaction results in the three stars simply rearranging their orbits, but in a specific high-energy scenario, one of the stars can absorb a massive gravitational kick. It works like this: the two stars in the tight binary act as a single, massive gravitational pivot. As the third star swings by, it transfers a tremendous amount of kinetic energy to the binary pair, causing them to swing closer together in a tighter orbit. To conserve energy and momentum, that energy has to go somewhere, and it gets funneled into the third star, accelerating it to a phenomenal speed. It's the cosmic equivalent of cracking a whip. The handle moves a little, but the very tip is launched forward at a supersonic crack. In a septuple system, which is essentially a series of nested three-body problems, the conditions for this kind of ejection are not just possible, they are statistically inevitable over billions of years. The ejected star doesn't just drift away, it is flung out like a bullet from a rifle, often reaching speeds exceeding 1,000,000 miles per hour. At that velocity, the star becomes a hypervelocity object, a lone wanderer on a one-way trip through the galactic halo. What's left behind in the Septuple system is equally changed. The ejection is a traumatic event that removes a significant amount of mass and energy from the system's core. The remaining stars recoil from the interaction, their orbits permanently altered, potentially becoming more eccentric or even unstable. A system that was once a septet might be permanently reduced to a sextet, a quieter but forever changed family. This process provides a compelling explanation for some of the isolated, high-velocity stars we see far from any obvious birthplace, suggesting that the frantic activity within these dense stellar systems is a key contributor to the population of lone wolves racing through the darkness of interstellar space. While the violent gravitational tides within the inner sanctum of a septuple system seem to spell doom for planet formation, astronomers have made a surprising and counterintuitive discovery. Many of these systems are actually surrounded by colossal, dusty debris disks. These are not the calm, orderly protoplanetary disks where planets are born around infant stars. These are something else entirely. They are the chaotic aftermath, the cosmic junkyards filled with the pulverized remains of asteroids and comets that either never managed to coalesce into planets or were utterly destroyed after they formed. The presence of these vast rings of dust and ice is a testament to the immense destructive power of the system, but it also hints at a more subtle truth, that even in this turmoil, the basic ingredients for building worlds are present. The sheer scale of these disks is difficult to comprehend. Imagine a ring of debris so vast it could easily engulf the entire orbit of Pluto in our own solar system. A disk containing not just fine dust, but countless asteroids, moonlets, and icy bodies all colliding with each other in a perpetual demolition derby. What makes these disks in septuple systems so strange, however, is their shape. Instead of being flat, pristine rings like Saturn's, they are often warped, puffed up, and twisted into bizarre configurations. This distortion is a direct result of the gravitational orchestra conducting from the center. With 7 stars pulling in different directions at different times, the disk cannot settle into a peaceful, stable plane. The gravitational perturbations act like a constant stirrer, preventing the dust and gas from calming down and organizing itself. A particle attempting a simple, circular orbit finds itself constantly nudged, its path altered by the passing gravity of one stellar companion after another, ensuring the disk remains a turbulent, three-dimensional cloud rather than a thin, construction-friendly sheet. This constant stirring presents the ultimate obstacle to planet formation. The process of building a planet is a gentle one, starting with microscopic dust grains gently sticking together through static electricity, gradually growing into pebbles, then rocks, and eventually planetesimals, the building blocks of planets. This requires a serene environment where these tiny objects can collide at slow speeds and stick together. But in the chaotic disk of a septuple system, the gravitational perturbations impart high velocities to every particle. Collisions are not gentle mergers, they are hypervelocity impacts that shatter objects into finer dust than before. It's the difference between trying to build a snowman in a gentle snowfall versus trying to do it in the middle of a blizzard with hurricane-force winds. For a long time, this led to the conclusion that these systems must be planetary dead zones, places where the chaotic environment makes the birth of a true, Earth-like planet an impossibility. Yet, nature has a remarkable talent for finding pockets of calm within the storm. The key lies once again in the system's hierarchical structure. While the inner regions are a gravitational maelstrom, astronomers have identified potential stable zones much farther out. The most promising of these is a region orbiting the entire central cluster of stars. At this immense distance, the complex individual tugs of the 6 inner stars average out. A dust grain or a small planetesimal here would essentially feel the gravitational pull of a single, combined mass at the system's center. In this quiet gravitational harbor, the chaotic stirring is minimized. The orbital periods are so long that the disruptive influences from the central stars become gentle, rhythmic nudges rather than constant, violent shocks. It is in these distant, placid rings that the traditional process of planet formation might still have a fighting chance. Dust could gently coalesce, pebbles could slowly accumulate, and over hundreds of millions of years, a planetesimal could grow in peace, protected by sheer distance from the frenetic activity at the heart of its stellar family. The evidence for this comes from detailed observations of the debris disks themselves. By analyzing the infrared light emitted by the warm dust, astronomers can map the disk's structure and temperature. In some systems, they detect signs of gaps and rings within the disk clearings that suggest the presence of unseen, shepherding bodies. Just as Neptune's gravity clears a path in the Kuiper belt of our solar system, a newly formed planetesimal, or even a full-grown planet, orbiting in one of these stable zones could be gravitationally sweeping its orbit clean of smaller debris, creating a dark band in the otherwise bright disk. This is the tantalizing clue that planet formation might not be completely impossible in these extreme environments. It simply requires a different blueprint, one where worlds are forged not in the warm inner glow of a single star, but in the cold, distant outskirts under the combined faint light of a septuple sun. But the chaos within these systems isn't just visible as distorted starlight. It screams across the electromagnetic spectrum in the most energetic voices known to physics. When astronomers point space-based observatories like NASA's Chandra X-ray Observatory or the Fermi Gamma-ray Space Telescope toward a septuple star system, they don't see a quiet collection of suns. Instead, they detect brilliant, flickering beacons of high-energy radiation, signals so powerful they reveal processes far more violent than the gravitational dances we've discussed. These are the X-ray and gamma-ray emissions, the death cries of matter being subjected to forces of almost unimaginable intensity, and they point to a specific, destructive relationship unfolding within the stellar family. The primary engine for this high-energy fury is a phenomenon known as an X-ray binary, but operating here within the ultimate crowded neighborhood. The scenario begins with the starkly different life cycles of the stars in the system. Recall that these families contain stars of all masses and ages. You might have an elderly, dense stellar corpse like a white dwarf or a neutron star orbiting perilously close to a younger, bloated red giant. If they are part of one of the system's tight inner binaries, the stage is set for a cosmic vampire act. The immense gravity of the dense, dead star begins to literally strip material away from the atmosphere of its giant companion. This stream of gas doesn't fall directly onto the surface. Instead, it spirals inward at velocities approaching a significant fraction of the speed of light, forming a superheated disk of plasma around the dense star known as an accretion disk. The temperatures within this disk are staggering, reaching millions of degrees Celsius. It is this incandescent, frenzied maelstrom of matter that blasts out X-rays, making the entire binary pair shine with an intensity that can outshine all 7 of the system's stars combined in visible light. What makes this process so extreme in a septuple system is the added instability provided by the other stars. The gravitational tides from the 3rd, 4th, and 5th stellar companions constantly jostle the accretion disk, disrupting the flow of material. This leads to wild, unpredictable variations in the X-ray output. Astronomers observe these sources flaring erratically, dimming suddenly, or erupting in sudden outbursts as a clump of material is shaken loose and plunges onto the neutron star's surface. It's a more chaotic and violent version of a process seen in isolated binaries, supercharged by the system's complex gravity. The most dramatic events occur when the recipient is a neutron star. With a gravitational field billions of times stronger than Earth's, the infalling gas impacts the star's solid surface or powerful magnetic field with the energy of a continuous nuclear explosion. In some cases, if the neutron star has a strong magnetic field, the incoming material is funneled onto the magnetic poles, creating incredibly hot spots that rotate into and out of our view like a cosmic lighthouse, detected as a regular, rapid pulsation in the X-ray signal. These high-energy revelations transform our understanding of these systems from merely gravitational curiosities into cosmic particle accelerators, where the simple act of matter falling under gravity creates some of the most luminous and volatile phenomena in the entire galaxy. This intricate balance of gravitational forces and hierarchical orbits pushes us to a fascinating frontier in astrophysics. What is the absolute maximum number of stars that can possibly form a single, bound system? If 7 star systems are rare, could nature produce an octuple, a nonuple, or even a system with a dozen stellar members? Scientists have turned to sophisticated computer simulations to answer this very question, modeling the chaotic birth and evolution of stellar nurseries under extreme conditions. These virtual experiments reveal that while septuple systems are at the bleeding edge of observed complexity, they may not represent the ultimate theoretical limit. The models suggest that under near-perfect conditions, an exceptionally dense and massive cloud of gas with minimal internal turbulence, a system with 8, 9, or even 10 stars could momentarily form. The key word, however, is momentarily. The stability of such a super-system would be astronomically fragile. Each additional star introduces a geometric increase in gravitational interactions, transforming the system from a hierarchical dance into a volatile gravitational free-for-all. The simulations show that systems with more than 7 stars exist in a state of perpetual crisis. They are so densely packed that the delicate separation of scales, which protects inner binaries from outside influence, begins to break down. The gravitational sphere of influence of one tight binary pair can start to overlap significantly with that of another, leading to constant disruptive encounters. A star from one pair might make a close pass by a star from another pair, exchanging gravitational energy in a way that sends one of them into a dangerously eccentric orbit, or even ejecting it entirely from the system. In these ultra-complex configurations, the 3-body interactions that occasionally eject a hypervelocity star from a septuple system would become the norm, not the exception. The system would essentially be tearing itself apart from within almost as quickly as it forms. This leads to a critical distinction between formation and longevity. A vast collapsing cloud might indeed fragment into a dozen or more cores that briefly become gravitationally bound. For a short time, perhaps only a few million years, a blink of an eye in cosmic terms, a 10-star system might exist. But its fate is almost certainly sealed. The slightest perturbation, whether from the stellar winds of its most massive members or the gravitational tug of a passing star from outside the system, would be enough to trigger a chain reaction of ejections. The system would rapidly decay, shedding stars until it reached a simpler, more stable configuration, likely a quintet or sextet that could survive for billions of years. This means that while an octuple system might be born, its life would be spectacularly short, making the chance of us observing one in the present-day galaxy infinitesimally small. The septuple systems we have found are therefore the survivors, the rare cases that achieved a stable equilibrium. They represent the practical upper limit for long-term stability in our universe. But the high-energy fireworks and gravitational chaos we've discussed are just part of the story. To uncover the deepest secrets of these systems, astronomers turn to a more subtle art, stellar spectroscopy. By carefully analyzing the specific colors of light emitted by each star, they can determine its chemical composition, almost like taking a cosmic blood sample. And in the case of septuple stars, this chemical analysis has revealed something profoundly strange. The surfaces of these stars often show bizarre and unexpected abundances of certain elements, with ratios of lithium, carbon, and oxygen that defy the standard rules of stellar evolution. These peculiar chemical signatures are not random errors. They are the ghostly fingerprints of dramatic, violent events that occurred billions of years ago, permanent scars from a history of cosmic cannibalism. In a normal, isolated star, its surface chemistry tells a predictable story. A star is born with a specific set of elements inherited from the interstellar cloud that formed it. As it ages and fuses hydrogen into helium in its core, the surface composition remains largely unchanged, a pristine record of its birth. But in the crowded confines of a septuple system, this simple narrative is torn to shreds. The culprit is once again unstable mass transfer. When one star in a tight binary pair swells into a red giant, its outer layers become gravitationally vulnerable. If it has a close companion, that companion can siphon off a significant portion of its atmosphere. This stream of stolen gas, rich in the specific elements forged deep within the donor star, then rains down onto the surface of the receiving star. This process permanently alters the recipient's chemical identity. Imagine a painter who only works with blue and yellow suddenly having a bucket of bright red paint thrown onto their canvas. The resulting color is something entirely new and unexpected. That's what happens to a star that receives a transfusion of material from its partner. For instance, a star might be found with an abnormally high amount of carbon on its surface. This is a telltale sign that it was once the recipient in a mass transfer event, absorbing the carbon-rich outer layers of a more evolved companion that had already fused helium into carbon in its core. The receiving star, which should have a normal, sun-like composition, is now chemically polluted, its original surface signature overwritten by the remnants of its neighbor. The case of lithium is particularly puzzling. Lithium is a fragile element that is easily destroyed in the hot interiors of stars. In most sun-like stars, it is conspicuously absent from the surface, having been burned up early in the star's life. So, when astronomers detect significant amounts of lithium on a star's surface in a septuple system, it sets off alarm bells. This lithium shouldn't be there. Its presence is a major clue that the star has recently acquired fresh material from the outside. The leading theory suggests that the process of mass transfer itself can actually create new lithium. The tremendous temperatures and pressures in the region where the stream of gas impacts the surface of the receiving star can trigger nuclear reactions that are not possible in a star's calm interior, briefly forging new lithium atoms in a process called cool bottom burning. The star becomes both the recipient and the factory, its surface enriched with an element that is a clear marker of a recent, violent interaction. These chemical anomalies do more than just confirm that mass transfer happened. They allow scientists to piece together the system's history with forensic detail. By comparing the chemical signatures of different stars within the same septuple system, astronomers can work backwards to identify which stars were the donors and which were the recipients. They can estimate how much material was transferred and even approximate when the event occurred in the system's long history. A star with a strong signature of carbon enrichment likely had a mass transfer event more recently than one where the signatures have been mixed back into the star's interior over time. This turns the entire system into a layered archaeological site, with each star's atmosphere holding a chapter of a shared violent past. These peculiar chemical abundances are therefore not just oddities. They are the primary evidence that these complex gravitational dances are not just orbital, but intimately physical, with stars literally reshaping each other's very substance across billions of years. This brings us to a truly radical idea that challenges our very understanding of how these stellar families are born. We've been exploring the intricate hierarchy of septuple systems as if they were all self-contained units, forming from a single collapsing cloud of gas. But what if that's not always the case? What if some of these cosmic families are not blood relatives, but rather adopted families assembled through a series of chance encounters? This is the core of the flyby perturbation hypothesis, a theory suggesting that the universe can build its most complex structures not just through quiet collapse, but through a violent game of gravitational billiards in the crowded cores of star clusters. To understand this, we need to step back and consider the environment where most stars are born, dense stellar nurseries. These are not serene places. They are chaotic, bustling cities of young stars, packed together thousands of times more densely than in our own quiet galactic neighborhood. In such a packed environment, close encounters between star systems are not rare events, they are commonplace. A young binary or triple system sailing through this cluster will inevitably pass near other systems. Normally, these flybys are fleeting. The stars approach, their gravity slightly alters each other's paths, and they continue on their way. But under very specific conditions, something far more dramatic can occur, a gravitational capture. Imagine a young quintuple star system, itself a rarity, moving through the cluster. It has a complex but stable hierarchical structure. Now imagine a stray binary pair, two stars bound together, on a trajectory that brings them exceptionally close to the quintuple system. As they pass, the gravitational forces between all 7 stars become a tangled web. Energy and momentum are exchanged in a frantic dance. In most scenarios, the binary pair would be slingshotted away, perhaps with a slightly altered speed. But in a perfect, delicate balance, the interaction can rob the binary pair of just enough energy that they cannot escape. Instead of flying away, they become gravitationally bound to the quintuple system, settling into a wide, stable orbit around the existing cluster. In one fleeting moment, a quintet becomes a septet. The system wasn't born with 7 stars, it acquired them through a cosmic merger. So, how do we find evidence for such an ancient, dramatic event? The clues are written in the geometry of the orbits themselves. In a system that formed from a single cloud, you would expect a certain degree of order. While the orbits wouldn't be perfectly aligned, there would be a tendency for them to share a similar overall orientation, a relic of the original cloud's spin. But if a system was assembled piecemeal through flybys, the orbital planes of the captured stars could be wildly misaligned compared to the original family. They would be like new guests arriving at a party from a completely different direction, bringing their own unique angle of approach with them. Astronomers search for this evidence by meticulously mapping the orbital inclinations of each stellar component. Using a combination of radial velocity measurements, astrometry, and the complex patterns in the system's light curve, they can reconstruct the tilts of the various orbits relative to our line of sight and to each other. In some candidate septuple systems, they find exactly this kind of chaos. The inner core of 4 stars might have orbits that are roughly coplanar, suggesting they formed together. But the wider binary pair and the solitary 7th star orbit on planes that are severely tilted, even perpendicular to the inner group. This is a huge red flag. It's extremely difficult for a single collapsing cloud to naturally produce such dramatically misaligned orbits. The simplest explanation is that these oddly orbiting stars are interlopers, captured long ago, and whose unique orbital angles are a permanent record of the direction from which they arrived during that fateful flyby billions of years in the past. This hypothesis transforms our view of these systems from static islands of stability into dynamic entities with a history of interaction. It suggests that in the dense urban centers of globular clusters or young associations, star systems can grow by accreting their neighbors. This flyby assembly line might even be a primary mechanism for building the highest order multiples we see, offering an explanation for why systems of 7 stars are so incredibly rare. They require not just a perfect birth, but a perfect series of cosmic mergers. It paints a picture of a far more sociable and interactive universe where stellar families are not always born but can be made. Now we come to one of the most subtle and yet most definitive pieces of evidence that reveals the true complexity of these systems, the phenomenon of apsidal precession. To understand this, picture a single star orbiting another in a perfect, stable ellipse. This ellipse has a fixed orientation in space with a point called the periastron where the stars are closest together. In a simple, isolated binary system, this ellipse remains rock solid, an unchanging celestial track that the stars follow cycle after cycle. But introduce just one more gravitational influence, a third star, and something fascinating happens. The immense pull of that third body acts as a constant, gentle tug on the ellipse itself, causing the entire orbital path to slowly rotate, like a hula hoop spinning around a dancer's waist. This gradual rotation of the orbit's orientation is what astronomers call apsidal precession. In a typical triple system, this precession is slow, steady, and predictable. It's a smooth, clockwork motion that can be calculated with exquisite precision. But in a septuple star system, this orderly process is thrown into utter chaos. Instead of a single distant perturber, each star is subjected to a relentless barrage of gravitational tugs from not one, but 6 other massive bodies, all pulling from different directions and at different strengths, depending on their ever-changing positions. The result is that the elliptical orbit of any given star doesn't experience a smooth, uniform precession. Instead, it wobbles, jerks, and stutters. The orientation of its ellipse changes in a wildly erratic and unpredictable manner, a clear and unmistakable signature that the simple model of a binary or triple system is completely inadequate. This erratic wobble is not a bug. It's the feature that allows astronomers to confirm the presence of all 7 bodies. By meticulously tracking the precise timing of eclipses over many years, scientists can detect these tiny, irregular shifts in the orbits. If a star's orbit were fixed, its eclipses would occur with metronomic regularity. But when apsidal precession is at work, the timing of these eclipses drifts. They occur slightly early or slightly late, in a pattern that directly maps onto the rotation of the orbit. In a septuple system, this timing drift is a tangled mess of overlapping signals. It's the gravitational equivalent of listening to 7 different songs playing at once and trying to identify each instrument. Supercomputers are tasked with running millions of simulations, testing different combinations of stellar masses and orbits, until they find the one unique configuration of 7 stars that perfectly reproduces the observed chaotic dance of the precessing orbits. It is this incredible mathematical detective work, decoding the gravitational whispers of apsidal precession, that provides the final, indisputable proof that we are indeed looking at a system of 7 stars bound in an intricate, ever-changing gravitational embrace. Yet, even with 7 confirmed stars, the census of a septuple system might not be complete. Lurking in the vast spaces between these brilliant suns could be hidden, failed members of the family, objects known as brown dwarfs. These cosmic in-betweeners are too massive to be considered planets, yet too small to ignite the sustained nuclear fusion that defines a true star. They are, in essence, stellar embryos that never quite made it, cooling and fading into obscurity over time. Their faintness makes them incredibly difficult to detect, especially when lost in the overwhelming glare of 7 bright stars. The ongoing hunt for these dim objects is one of the most challenging quests in modern astronomy, pushing our observational technology to its absolute limits. The primary tool in this search is infrared light. While a brown dwarf emits very little visible light, it glows with a dull red heat from the residual energy of its gravitational collapse. Powerful space-based observatories like the James Webb Space Telescope are perfectly equipped for this task, their infrared cameras acting as heat-sensitive scopes that can peer through the glare of the primary stars to spot the faint, warm signature of a brown dwarf companion. The search is a meticulous process of subtraction. Astronomers first create an incredibly detailed model of the light expected from all 7 known stars. They then compare this model to the actual infrared light received from the system. Any persistent, unexplained excess of infrared radiation could be the telltale sign of a hidden, warm body orbiting within the system's gravitational grip. Discovering a brown dwarf in a septuple system would be far more than just adding another member to the family. It would have profound implications for our understanding of how stars form in the most extreme environments. Astronomers use a concept called the initial mass function, which is essentially a cosmic rulebook describing how a collapsing cloud of gas and dust partitions its mass. In a typical stellar nursery like the one that gave birth to our Sun, this function predicts that you'll get a few very massive stars, a larger number of medium-sized stars like our own, and a vast multitude of tiny, faint red dwarfs and brown dwarfs. It's a predictable distribution, but does this rulebook still apply in the frantic, ultra-dense environment that spawns a septuple system? Finding a brown dwarf there would suggest that even under such extreme conditions, the cloud still fragments all the way down to the lowest mass objects. It would indicate that the star formation process is robust and universal, capable of producing the full spectrum of stellar and substellar bodies regardless of the gravitational chaos. Conversely, if a thorough search of multiple septuple systems reveals a surprising absence of brown dwarfs, it would point to a dramatically different scenario. Perhaps in these crowded nurseries, the gravitational turmoil is so intense that the collapsing cloud is only able to form larger, more massive fragments, effectively truncating the low mass end of the initial mass function. The presence or absence of these failed stars is therefore a critical test, a piece of evidence that tells us whether the universe's recipe for building stars is one size fits all, or if it has a special, more exclusive menu for its most extravagant gravitational families. While the spectacular supernova and stellar collisions within septuple systems dominate our attention, there is a far more subtle, almost imperceptible vibration being generated by these cosmic families. A vibration that travels not as light, but as a ripple in the very fabric of spacetime itself. This leads us to a profound discovery that connects these rare stellar groupings to one of the most ambitious listening projects in the history of science, the hunt for gravitational waves. We are accustomed to the idea of observing the universe, but now we are learning to hear it, and septuple systems have a distinct, albeit faint, voice in the cosmic chorus. The primary source of these ripples is the slow, inexorable death spiral of compact stellar remnants. Within the intricate hierarchy of a septuple system, the end stages of stellar evolution often leave behind incredibly dense pairs. Imagine two white dwarfs, the Earth-sized cores of dead stars, or even two neutron stars, each a city-sized object more massive than our Sun, locked in a tight binary orbit. According to Einstein's theory of general relativity, such massive objects in accelerated motion will radiate energy away in the form of gravitational waves. This energy loss has a direct consequence. It causes the two objects to gradually lose orbital energy, drawing them closer together in an ever-tightening spiral that can last for billions of years. It is this slow, cosmic inspiral that generates a continuous, low-frequency hum of gravitational radiation. Now, the crucial point is that no single septuple system is close enough or loud enough for our current detectors, like LIGO and Virgo, to pick out its individual signal. The gravitational waves from such a system are incredibly weak by the time they travel across hundreds or thousands of light years to reach us. They are a whisper lost in the cosmic wind. However, this is where the concept of the stochastic gravitational wave background becomes essential. Think of yourself standing in a vast, crowded stadium. You cannot hear the specific conversation of any single person sitting on the opposite side, but you are still immersed in a constant, pervasive roar, the combined sound of tens of thousands of individual voices. That collective roar is the analog of the stochastic background. It is not a single signal, but the overlapped hum from every inspiraling binary system of compact objects throughout the entire universe. This is where the unique role of septuple systems comes into sharp focus. While they are incredibly rare, their internal dynamics make them extraordinarily efficient factories for producing these binary pairs of compact objects. The complex gravitational interactions within a septuple system seem to funnel stellar evolution toward these dramatic endpoints. The same processes that can lead to stellar cannibalism and chaotic mass transfer also create the perfect conditions for pairing up white dwarfs and neutron stars. Because of their hierarchical stability, these pairs can then inspiral for eons without being disrupted, continuously contributing their specific frequency to the universal hum. By studying the population and properties of septuple systems, astronomers can make a critical estimate just how many such tight, inspiraling binaries exist in the cosmos. This allows them to build a more accurate model of what the total gravitational wave background should sound like. The significance of this modeling cannot be overstated. As our gravitational wave observatories become more and more sensitive, their next great challenge is to detect this faint background hum. It is the holy grail of low-frequency gravitational wave astronomy. Confirming its existence and, more importantly, matching its strength and frequency spectrum to our predictions would provide a monumental test of our understanding of stellar evolution on a cosmological scale. If the observed background is stronger than our models predict, it would be a clear sign that we are missing something, that there are more sources of gravitational waves out there than we thought. Perhaps septuple systems are even more common than we realize, or maybe other, even more exotic phenomena are at work. Conversely, if the background is fainter, it would force us to reconsider the very processes that create and sustain these tight binary systems. In this way, the silent, rhythmic dance of dead stars in distant septuple systems provides the essential sheet music that allows us to tune our ears to the deepest, most fundamental vibrations of the universe. This intricate dance of gravitational waves brings us to a puzzle that strikes at the very heart of how we measure the age of stars, a puzzle that becomes exponentially more confusing when set against the backdrop of a septuple system. It's known as the Algol paradox, a classic head-scratcher in astronomy that is transformed into a bewildering web of contradictions when you have 7 stars to contend with. The original paradox is named after the star system Algol, also called the demon star, where observers noticed something that seemed to violate the basic rules of stellar life cycles. In a binary pair, the more massive star should always evolve faster, using up its nuclear fuel and aging into a red giant long before its lighter companion. Yet in Algol, the more massive star was still a hot, young main sequence star, while its less massive partner was already an old, bloated subgiant. It was as if a child appeared to be older than its parent. The solution to this paradox is mass transfer, a process we now know is rampant in septuple systems. The explanation is that the stars were born at the same time following the normal rules. Initially, the star that is now the less massive, older-looking one was actually the more massive of the two. It lived its life so quickly that it exhausted the hydrogen in its core and began to swell into a red giant. As it expanded, it crossed a critical boundary where its outer layers became gravitationally dominated by its companion. Over millions of years, a huge portion of its mass, its very stellar substance, flowed onto the other star. The donor star was stripped down to its hot, evolved core, looking old and aged, while the recipient star was bulked up with fresh hydrogen fuel, making it appear younger, hotter, and more massive than it truly is. The stellar identities were swapped, creating an evolutionary illusion. Now, take this single, mind-bending paradox and project it onto the 7-star stage. In a septuple system, this isn't a one-time event confined to a single pair. It's an ongoing cycle of cosmic identity theft that can involve multiple stars across different hierarchical levels. Imagine trying to date this stellar family. You point your spectroscopes at each star, measuring their temperatures, luminosities, and compositions to estimate their ages. What you find is a chronological nightmare. A massive, brilliant blue star in one tight binary might appear to be a youthful 10 million years old, while its direct, less massive binary partner looks like a 5 billion-year-old relic. Meanwhile, a star in a different binary pair orbiting the first one shows chemical signs of having been polluted by material from a third star that has since exploded. The entire system becomes a tangled mess of apparent ages that bear no relation to the system's true, unified birth date. This creates a complex web where simple age-dating methods completely break down. The standard technique of isochrone fitting, where astronomers compare a star's properties to models of how stars of a given mass evolve over time, becomes practically useless. You can't simply plot all 7 stars on a graph and draw a single line of equal age through them. The stars have been chemically and physically altered by their interactions. The massive ones have gained weight, the light ones have been stripped bare, and many have had their surfaces contaminated with elements forged inside their neighbors. A star that looks like it should be old might actually be young, and a star that appears youthful might be an ancient entity that simply stole a new lease on life. The system's history is not written in the present-day states of its stars, but in the subtle forensic clues of their chemical anomalies and orbital dynamics. Untangling this web requires piecing together a narrative of successive mass transfer events, a cosmic archaeology project that reveals a history of stellar cannibalism and rebirth far more dramatic than anything we see in simpler systems. But the high-energy drama of a septuple system is not confined to the brilliant glare of X-rays or the faint whispers of gravitational waves. Some of the most startling activity is revealed when astronomers tune their instruments to the relatively quiet radio portion of the electromagnetic spectrum. Here, in the realm of long wavelengths, they have detected something that defies easy explanation. Powerful, highly focused jets of material shooting out from the heart of these mature stellar families at a significant fraction of the speed of light. These are not the gentle outflows of solar wind we see from our sun. These are colossal, collimated beams, energetic enough to be seen across interstellar distances. The existence of such jets in a system that is billions of years old presents a profound mystery, as they are a phenomenon we almost exclusively associate with the extreme youth or the violent death of stars. Typically, we observe these precise jets in 2 very distinct settings. The first is in the earliest stages of star formation, where a newborn protostar is still gathering mass from a surrounding disk of gas and dust. As material spirals inward, powerful magnetic fields can channel some of it away from the poles, launching twin jets that punch through the surrounding nebula. The second, and even more powerful, setting is around black holes and neutron stars, where their immense gravity shreds a companion star, and the resulting accretion disk funnels material into narrow, relativistic jets. Both scenarios involve a single, dominant gravitational engine, a young star or a dense remnant, and a plentiful supply of fresh material. Finding such a jet in a complex system of 7 mature stars, where no single black hole has been confirmed, forces a radical rethinking of the conditions required to power these cosmic particle accelerators. The leading theory points to the same chaotic mass transfer processes we've discussed, but with a new, explosive twist. Imagine one of the tight inner binaries where a white dwarf or a neutron star is voraciously feeding on its giant companion. The stream of stolen gas forms an incredibly hot, magnetized accretion disk. In most binary systems, this material simply heats up and emits X-rays. However, in the turbulent environment of a septuple system, the constant gravitational nudges from the other nearby stars may be providing the crucial extra ingredient, a powerful stirring action that supercharges the entire process. This external perturbation could warp the inner parts of the accretion disk, amplifying its magnetic fields to extraordinary strengths. These intensified fields then act like the barrel of a railgun, collimating a portion of the infalling plasma and launching it out along the system's rotational axis in a tightly focused jet, which we then detect as a strong source of radio waves. An even more exotic possibility involves not one, but two stellar remnants in a tight orbit. Consider a binary system consisting of two white dwarfs spiraling closer together due to gravitational wave emission. If they are part of the septuple's inner sanctum, a third star could make a close pass, triggering a premature merger. The collision of two white dwarfs is a cataclysmic event that can lead to a supernova. But in some cases, if the total mass is just below the critical threshold, it might instead form a rapidly spinning, extremely magnetic neutron star, a magnetar. This newly born hypermagnetic engine, suddenly immersed in a gas-rich environment from the other stars, could instantly begin powering jets of unbelievable power. The radio jets we see could therefore be the birth cry of a new kind of stellar remnant, one born not from a solitary supernova, but from a merger orchestrated by the complex gravitational dance of its stellar siblings. This suggests that septuple systems are not just stable configurations, they are potential crucibles for creating some of the most magnetically violent objects in the universe. Yet the very chaos that seems to forbid life might also be the key to creating environments where it could take hold in ways we can scarcely imagine. We must completely rethink the concept of a habitable zone. In our solar system, it's a rather simple, well-defined shell around the Sun, a region where water can potentially exist as a liquid on a planet's surface. But in a septuple system, this idea shatters and reforms into something far more complex and dynamic. You cannot have a single, circular habitable zone when you have 7 different sources of heat and light, each with its own intensity and orbital path. Instead, the habitable zone becomes a shimmering, evolving volume of space, a constantly shifting region where the combined stellar flux from multiple suns temporarily creates the right conditions for liquid water. The most intriguing possibility lies not in a planet orbiting a single star within the system, but in one that orbits the entire central cluster. Far beyond the frenetic gravitational dance of the inner binaries, a planet could find a stable path around the system's collective center of mass. From this distant vantage point, the 6 or 7 stars would appear relatively close together in the sky, their individual motions blending into a slow, stately dance. The planet's year would be incredibly long, perhaps spanning centuries, but its seasons would be dictated by its changing proximity to this combined stellar heart. The habitable zone in this scenario is not a gift from one star, but a shared offering from several. A planet here wouldn't rely on the steady warmth of a single sun-like star. Its light and heat would be a blended cocktail, a perpetual multi-source illumination. Imagine the sky from such a world, which we might call a Polarissima. There would be no true night, only a cycle of complex twilights. As one star set, another would already be rising, ensuring the sky is never completely dark. The light would be an ever-changing blend of colors, the golden hue of a sun-like star, mixing with the harsh blue-white glare of a hotter, more massive companion. Shadows would be soft and multiplied, casting faint, overlapping silhouettes from every object. The climate would be remarkably stable over short terms, as the combined light of multiple stars would smooth out the variations, but over centuries, as the stellar configuration slowly changed, the planet would experience grand climatic cycles unlike anything on Earth. It would be a world of perpetual, gentle daylight, a place where life would never know the profound darkness of a starless night. But the potential for habitability becomes even stranger when we consider the effects of this multi-sun environment on photosynthesis. On Earth, life's primary energy source is tuned to the specific spectrum of our solitary G-type star. On a world bathed in the combined light of stars of different types, some red and dim, others blue and intense, the evolutionary pressure on any photosynthetic organism would be completely different. Plants might evolve to be black, absorbing every possible wavelength of light from their multiple suns for maximum efficiency. or they might develop leaves that can dynamically adjust their pigments to best capture the dominant light source at any given moment as the stars shift in their sky. The very rhythm of life would be unshackled from a 24-hour cycle. With no true day or night, biological clocks could drift or disappear entirely, leading to ecosystems that operate on a continuous, slow rhythm dictated by tidal forces or atmospheric changes rather than a rising and setting sun. The possibility of life in such a system forces us to expand our definition of habitable to include worlds that are not just warmed by a single star, but gently cooked in the combined glow of a stellar family. But all of this intricate internal activity raises a question about the system's journey on a much grander scale. When we track the motion of stars across our galaxy, we typically observe a smooth, predictable path, a reflection of their orbit around the Milky Way's center. However, for some septuple systems, their movement tells a far more dramatic story. Their trajectory across the sky, a measurement astronomers call proper motion, reveals them to be runaway stellar families hurtling through space on a path that suggests a violent expulsion from their birthplace. This peculiar motion isn't a gentle drift, it's a high-speed flight, a clue etched in their velocity that points to a traumatic past event. The most likely explanation for this cosmic eviction is a gravitational slingshot encounter of staggering proportions. Imagine the young septuple system still nestled in the dense star-forming cluster where it was born. In such a crowded environment, close encounters with other massive star systems or even solitary black holes are not just possible, they are inevitable. If our septuple system had a close brush with a much more massive object, the gravitational interaction would have been intensely asymmetric. The more massive object would have barely felt a tug, but the septuple system, like a pebble kicked by a boot, would have been sent flying. This is the essence of a gravitational slingshot. Energy is transferred, accelerating the smaller system to a tremendous speed and often ejecting it entirely from the gravitational well of its birth cluster. What we are witnessing, then, is not just a family of stars, but a family in exile, a tight-knit group cast out into the galactic wilderness, destined to wander the interstellar void alone. The trajectory of these runaway systems allows astronomers to literally trace their path backwards through time. By meticulously measuring their current velocity and direction, scientists can project their movement across millions of years, like running a film in reverse. In several compelling cases, these backward tracks lead directly to the heart of known massive star clusters. This is the observational proof that these septuple systems are indeed escapees, their high proper motion a permanent record of the explosive event that launched them on their galactic journey. This discovery adds another layer of dynamism to their story. They are not static islands, they are voyagers. Their incredible internal stability, which allows them to survive as a septet, is what also enables them to endure this galactic ejection intact. A looser group of stars would have been torn apart by the same gravitational forces that expelled it. The fact that they remain bound together while racing across the galaxy is a testament to the resilience of their hierarchical gravitational bonds. They travel as a unit, a self-contained celestial city-state, carrying the secrets of its chaotic birth within it as it journeys through the vast, empty spaces between the stars. Now, let's venture out to the very fringes of such a system, to the cold, dark realms where the influence of its 7 suns grows faint. In our own solar system, this boundary is marked by the Oort cloud, a vast spherical shell of icy planetesimals surrounding us at a distance of nearly a light year. This is the deep freeze of our planetary family, a reservoir of ancient, pristine comets that only occasionally get nudged inward on long, looping orbits. If a world like our hypothetical Polarissima exists in a septuple system, it would almost certainly possess a similar cloud of its own. But the existence of this analog would come with a terrifying consequence. It would be subjected to a gravitational bombardment of unimaginable frequency, turning the inner system into a cosmic shooting gallery. The stability of our solar system's Oort cloud relies on the profound quiet of our galactic neighborhood. The gentle, steady pull of the sun holds it together, and only rarely does a passing star or the subtle tidal force of the Milky Way's disk give one of these icy bodies a push into the inner solar system. In a septuple system, that serene stability is a fantasy. The complex gravitational field created by 7 stars, all moving on different orbits, acts like a constant and unpredictable series of tremors shaking the entire outer solar system. Each time the stellar configuration changes, which is continuously, the gravitational tides washing through the Oort cloud analog shift and ripple. A comet that was in a stable orbit for millennia might suddenly find itself in a path that sends it careening directly toward the inner planets. This leads to an influx of comets so high that it would be a perpetual storm. Instead of a spectacular comet appearing once every few decades or centuries, the inner system would be under a near-constant rain of these icy visitors. The sky would be frequently streaked with multiple comets, some glowing brightly as they swing close to the combined heat of the stars. While this might create a beautiful celestial display, the practical implications for any emerging life would be catastrophic. The constant bombardment would pose an existential threat, with large impacts occurring on a timescale that would prevent complex life from ever gaining a foothold. It's a scenario that makes the asteroid impact that ended the reign of the dinosaurs look like a minor event in a relentless cycle of destruction. The dynamics of this are further complicated by the system's hierarchical structure. The innermost tightly bound pairs of stars have a very localized gravitational effect, but the wider stellar companions, particularly the solitary 7th star on its immense orbit, are the real drivers of this chaos. As this distant star swings through the outer reaches of its multi-thousand-year orbit, its gravity would dominate the outer Oort cloud, stirring it up like a spoon in a bowl. Each close pass would scatter countless comets into the inner system, an event that would last for centuries. The planet's long, stable climatic periods would be punctuated by these eras of intense bombardment, each one potentially triggering a mass extinction event that would reset the evolutionary clock. Life, if it could persist at all, would have to be incredibly resilient, perhaps hibernating deep underground or in the planet's oceans to survive these episodic apocalypses. The very existence of a rich Oort cloud, which in our system is a source of occasional wonder, becomes in a septuple system a permanent sword of Damocles hanging over any world that dares to harbor life. But does this incredible complexity exist only here in our own Milky Way galaxy? For a long time, that was an open question, as spotting such a faint, compact system even within our galactic neighborhood pushed our telescopes to their limits. The truly groundbreaking discovery, however, is that these gravitational marvels are not a local oddity. Astronomers have now begun to find tentative evidence of septuple star systems in other galaxies, confirming that the universe's recipe for building stars can produce these intricate families on a truly cosmic scale. The most promising searches have focused on our galactic neighbors, like the Large and Small Magellanic Clouds. These dwarf galaxies are close enough that their individual bright stars can be studied, yet they offer a completely different environment from our own Milky Way. They are smaller, have a lower overall concentration of heavy elements, and represent a distinct type of galactic architecture. Finding a septuple system in a place like the Large Magellanic Cloud is a task of monumental difficulty. It relies on the same techniques used locally, meticulously monitoring the light curves of suspiciously variable stars, but from a distance of about 160,000 light-years. At that range, what appears as a single point of light to even the most powerful telescopes could easily be a dense cluster of stars. The identification is therefore statistical and probabilistic. Astronomers look for complex, non-repeating patterns of dimming and brightening that are mathematically consistent with the overlapping eclipses of multiple stars in a hierarchical orbit. When they find a candidate whose light curve is so bizarre that it cannot be explained by anything simpler than 5, 6, or even 7 components, they have likely found an extragalactic septuple system. These are still considered tentative identifications, but they are the first crucial hints that our galaxy does not hold a monopoly on stellar extravagance. The profound importance of these distant discoveries lies in their power to test the universality of our formation theories. If septuple systems can only form in large, metal-rich galaxies like the Milky Way, that would tell us that their creation depends on a very specific set of ingredients. Perhaps the high dust content or the strong gravitational potential of a big galaxy is necessary to keep a collapsing cloud stable enough to fragment into 7 pieces. But if we find them in the smaller, more primitive Magellanic Clouds, it forces a dramatic rethink. It suggests that the fundamental physics of hierarchical fragmentation is so robust that it can operate even in environments that are poorer in the heavy elements thought to be crucial for efficient gas cooling and collapse. This would mean that the potential for such complex systems is woven into the very fabric of gravitational physics itself, a universal outcome wherever conditions are right, regardless of the specific galactic context. Each extragalactic septuple system found is another data point, another confirmation that the universe's capacity for creating wondrous and complex structures extends far beyond our own celestial backyard. But the gravitational forces that warp stars and dictate their orbits are not the only invisible power at play in this crowded celestial arena. There is another, equally potent force that is twisted and amplified by the frantic dance of these 7 suns: magnetism. Each star in the system is a roiling dynamo of plasma, its churning interior generating a powerful magnetic field that extends far out into space, much like the field that surrounds our own sun. In a solitary star, this field has a relatively simple dipole structure like a giant bar magnet. But place 7 of these magnetic powerhouses in close proximity, with their fields overlapping and interacting, and you create a magnetic environment of unimaginable complexity and ferocity. The turbulent interactions and the rapid, tidally locked rotations of the inner binaries act as a supercharger, taking the innate magnetism of each star and amplifying it to extremes. The consequences of these amplified fields are profound, transforming the space between the stars from a near vacuum into a region dominated by magnetic architecture. One of the most visible effects is on the stellar winds. Every star emits a constant stream of charged particles, a wind that blows outward in all directions. In our solar system, the solar wind travels in a relatively unimpeded flow. But in a septuple system, the magnetic fields from multiple stars act like invisible fences, channeling and confining these winds. Instead of expanding freely, the winds from one star are forced to flow along the magnetic field lines of its neighbors, colliding with other winds and creating colossal shock fronts where particles are accelerated to near light speeds. These confined winds can form intricate structures like magnetic tubes or bubbles that envelop entire groups of stars within the system, trapping radiation and creating hotspots of intense energy. This magnetic control extends dramatically to the process of accretion, where one star strips material from another. We already discussed the chaotic stream of gas flowing between close binary partners. But that stream is not simply falling under gravity. It is a conductor moving through a magnetic field. The powerful fields of the receiving star can seize control of the incoming material, forcing it to flow along specific magnetic highways directly onto the star's magnetic poles. This process, known as magnetically channeled accretion, is far more violent than its non-magnetic counterpart. The material, funneled into a narrow column, impacts the star's surface at a significant fraction of the speed of light, releasing a torrent of X-rays. The external gravitational nudges from the other stars in the system constantly jostle this delicate magnetic funnel, causing the accretion flow to sputter and flare erratically, turning a steady trickle into a series of violent, unpredictable downpours. The most spectacular manifestation of this magnetic turmoil is the potential for superflares. On our Sun, solar flares are impressive eruptions that can disrupt satellites and power grids. But they are mere firecrackers compared to what a septuple system can produce. The tightly wound magnetic fields in these systems are under immense stress, storing colossal amounts of energy. When the complex gravitational dance causes two magnetic field structures from different stars to interact, a process called magnetic reconnection, that pent-up energy is released in a cataclysmic instant. The resulting flare can be thousands of times more powerful than anything our Sun has ever produced. A flash of radiation so intense it would briefly outshine the combined light of all 7 stars in the system. For any hypothetical world orbiting within the habitable zone, such an event would be an existential threat, sterilizing the surface with a wave of high-energy particles and X-rays. The magnetic fields in a septuple system are therefore not just a curious side effect. They are a fundamental driver of the system's most violent and energetic behavior, adding a layer of electromagnetic chaos to the already overwhelming gravitational drama. But how do we know what these systems were like in their infancy? The answer comes from a special class of young stars that act as cosmic newborns, and finding them within a septuple system is like stumbling upon a nursery that's already arranged itself into a masterpiece of gravitational architecture. These stellar infants are known as T-Tauri stars. They are the newly formed pre-teen versions of stars like our Sun, still contracting under their own gravity and surrounded by the thick, swirling disks of gas and dust from which they were born. Finding a T-Tauri star is exciting because it gives us a snapshot of a star just a few million years into its life. But finding an entire system of them, already locked into the complex hierarchical dance of a septuple arrangement, is a discovery that fundamentally rewrites our timeline for how such intricate families are built. For a long time, the prevailing theory was that complex star systems formed in stages. A cloud would collapse, perhaps forming a tight binary or triple system first. Then, over millions or even tens of millions of years, this small group would slowly capture other passing stars through gentle gravitational interactions, gradually building up to a higher number like 7. It was thought to be a slow, patient process of cosmic assembly. The discovery of T-Tauri stars within a confirmed septuple system shatters that gradualist view. It tells us that the entire, breathtakingly complex hierarchy, the tight inner binaries, the orbiting pairs of pairs, and the distant 7th companion, can all be in place almost immediately while the stars themselves are still cosmic toddlers. The system is born whole, its intricate structure imprinted upon it from the very moment of its violent birth. This revelation forces us to reconsider the conditions inside the stellar nurseries that give rise to such wonders. The traditional picture of star formation involves a relatively orderly collapse of a gas cloud, fragmenting into a few large pieces. But to produce a septuple system of T-Tauri stars, the parent cloud must have been extraordinarily dense and turbulent, fragmenting not just into 2 or 3 pieces, but into 7 distinct cores that remained gravitationally bound in a precise hierarchical configuration from the outset. It suggests a process of hierarchical fragmentation within a hierarchy itself. The cloud didn't just split into 7 equal parts. It likely fragmented on multiple scales simultaneously, with smaller scale collapses happening within larger scale ones, directly creating the nested structure we see in mature systems. This isn't a slow assembly, it's a single, chaotic, and incredibly efficient event that forges a gravitational masterpiece in a geological instant. Observing these young systems is like watching the opening act of the drama we've been describing. The protoplanetary disks around each T-Tauri star are not serene, isolated construction zones. They are subjected to the same fierce gravitational tides from their multiple stellar siblings that will plague them for their entire lives. In these early stages, the effects are even more dramatic. The disks are massive and extended, making them highly vulnerable to gravitational disruption. Astronomers using radio telescopes can see the evidence of this chaos. The disks are often warped, truncated, or even torn into streamers of gas and dust flowing between the young stars. The environment is so hostile that the calm, gentle accumulation of dust needed to build planets may be nearly impossible in the inner regions. Yet, the very presence of these disks confirms that the raw materials for planets are there, setting the stage for the epic struggle between formation and destruction that will define the system's future. Finding T-Tauri stars in a septuple system doesn't just tell us how they form. It shows us the tumultuous starting conditions for everything that might come after, from planets to stellar collisions, all set in motion within the first few million years of their existence. This brings us to a peculiar census anomaly that has astronomers scratching their heads, a mystery that emerges only when you take a detailed inventory of the stellar residents within these complex families. Imagine meticulously weighing every member of a septuple system, expecting to find a smooth distribution from the heaviest giants down to the lightest dwarfs, a natural outcome of a cloud fragmenting into pieces of various sizes. Instead, in several of these systems, the data reveals a bizarre gap. You find a collection of low-mass stars, perhaps several red dwarfs, and then one or two stellar behemoths, but there's a conspicuous absence of stars in the middle weight category. It's as if the system has a missing link, a population of intermediate mass stars that should be there but simply aren't. This strange pattern isn't a random fluke. It's a potential fossilized clue, a direct hint about the specific and violent physical processes that govern the system's birth. To understand why this gap is so puzzling, we need to consider the standard model of star formation. In a typical stellar nursery, a collapsing cloud of gas breaks apart in a way that naturally produces more small stars than large ones. This is described by the initial mass function, which is like a universal rulebook for how cosmic building blocks are handed out. You get a few large bricks, a larger number of medium-sized ones, and a huge quantity of small pebbles. Finding a system that seems to have only the large bricks and the small pebbles, with the medium-sized ones entirely absent, suggests that the normal rulebook was thrown out the window during its formation. Something must have happened to either prevent medium-mass stars from forming in the first place, or to systematically remove them after the fact. One compelling explanation points to a phenomenon known as competitive accretion in an exceptionally dense environment. Picture the protocluster that would become the septuple system not as a calm, fragmenting cloud, but as a frantic, high-stakes scramble for material. In this scenario, multiple small cores form initially, all vying for gas from the same surrounding reservoir. However, the gravitational field is not even. The cores that happen to form in the deepest part of the gravitational well, or that start out slightly more massive, gain a decisive advantage. They act like gravitational vacuums, hoarding the incoming gas and growing rapidly, while their smaller, weaker siblings are starved of fuel. The intermediate mass cores are the ones that lose this competition most decisively. They are not small enough to go unnoticed, nor are they powerful enough to win the feeding frenzy. They are stuck in a gravitational no-man's land, unable to gather sufficient mass to become substantial intermediate stars, and eventually they might even be torn apart or merged with the growing giants. An even more dramatic possibility involves the concept of stellar collisions during the system's chaotic infancy. In the incredibly crowded conditions of the birth cluster, the orbits of the young protostars could have been much less stable than they are today. It's plausible that the system did originally form with a full spectrum of stellar masses, but a period of extreme dynamical instability followed. During this chaotic era, the intermediate mass stars, which would have been numerous and gravitationally influential, may have been the most likely victims of a cosmic game of bumper cars. Their orbits could have intersected, leading to direct mergers that created the single, high-mass stars we see today. Alternatively, A close gravitational encounter between two intermediate stars could have flung one out of the system entirely, a process known as ejection, while the other was thrown into a tighter orbit. This selective removal of the middle-weight stars would leave behind a bimodal population, the surviving merged high-mass beasts and the low-mass stars that were too small and nimble to be easily involved in the violent interactions. The mass gap we observe today would then be the silent echo of that ancient period of collisional chaos, a fossil record written not in rock, but in the present-day distribution of stellar weights. Now we turn our attention to a process so fundamental to the evolution of these dense stellar families that it might well be the mechanism that built them piece by piece. We've discussed how the complex gravitational tides in a septuple system can distort stars and lock them in a permanent embrace. But what happens when those same tidal forces act not on stars that are already bound, but on stars that are merely passing strangers? This is the realm of tidal capture, a gravitational seduction that can forge new stellar partnerships out of pure chaos. To grasp tidal capture, picture two stars that are not originally bound to each other. They are independent members of the system, perhaps on wide orbits that happen to bring them into a very close, but not quite capturing, encounter. As they swing past each other, their immense gravitational fields raise powerful tides on each other's surfaces. The star, being a fluid ball of plasma, doesn't remain perfectly spherical. It bulges towards the passing partner, like the ocean tide rising on Earth due to the Moon's pull. However, this process is not perfectly efficient. The energy required to flex and distort the star's shapes is dissipated as heat within their gaseous interiors. This dissipation acts as a cosmic brake, robbing the two stars of a tiny amount of their orbital kinetic energy. In a single, distant pass, this energy loss is negligible. But if the encounter is close enough, the tidal braking can be significant. It's the difference between two ice skaters gently brushing past each other and two skaters who grab hold of each other's arms as they pass, causing both to slow down and spin around a common center. That gravitational grab is tidal capture. The two stars, which had just enough energy to escape each other's pull forever, suddenly find themselves with insufficient energy to part ways. They become gravitationally bound, a new binary pair born from a fleeting moment of proximity. In the crowded core of a septuple system, where close passes are a regular occurrence, tidal capture is a powerful engine for creating new, intimate stellar relationships. This process sets the stage for something even more dramatic: exchange reactions. Imagine a pre-existing tight binary pair, two stars whirling around each other in a stable dance. Now introduce a third, single star on a trajectory that brings it exceptionally close to this binary. The resulting gravitational interaction is a frantic three-body problem. The single star doesn't just orbit the binary as a whole, it engages in a complex dance with each individual member. In the chaos of this close encounter, energy and momentum are traded between the three bodies in a way that is inherently unstable. Very often, the least massive star in the trio gets the short end of the stick. The most likely outcome is an exchange. The incoming single star, if it has enough mass and momentum, can gravitationally kick out one of the original binary members, taking its place. The ejected star is sent flying away on a new trajectory, perhaps into a wider orbit within the system or even out into interstellar space, while the new, more massive star settles into a stable orbit with the remaining partner. It's a celestial version of musical chairs, where the music is the relentless pull of gravity and a starker partner swap is hard to imagine. The original binary partnership is dissolved and a new one is formed, all in a cosmic instant. Within the nested hierarchy of a septuple system, these exchange reactions are not rare anomalies. They are a fundamental part of its long-term dynamic evolution. The system is a simmering pot of gravitational interactions, where the hierarchical structure provides stability on large scales but allows for localized chaos within the inner sanctums. A close pass between a wide binary pair and a third star could trigger an exchange that fundamentally alters the makeup of the inner core. A star that was once a distant companion could, through a series of such chaotic exchanges, work its way inward, replacing a star in one of the tightest, most dynamically important binaries. This process provides a dynamic pathway for stars to migrate within the system, explaining how a captured star from the outside could eventually find itself at the very heart of the gravitational dance, its presence a permanent record of a violent encounter that occurred billions of years in the past. Now we arrive at a discovery that transforms a classic tool of astronomy into a hypersensitive probe for measuring the hidden architecture of these systems. For over a century, astronomers have relied on pulsating variable stars like Cepheids and Aurora Lyrae stars as cosmic lighthouses. Their brilliance fluctuates with a remarkably steady rhythm, a pulsation driven by a delicate balance between gravity and radiation pressure in their outer layers. This predictable pulse makes them invaluable for measuring vast cosmic distances. But place one of these cosmic metronomes inside the gravitational whirlwind of a septuple system, and its steady beat begins to stutter and sway in the most revealing ways. The clockwork rhythm is perturbed by the relentless, changing gravitational tugs of its 6 stellar companions, and in those tiny, intricate irregularities lies a wealth of information about the system's deepest secrets. The mechanism is both subtle and powerful. Imagine a Cepheid variable star rhythmically expanding and contracting over a period of several days. As it breathes in and out, its precise pulsation period is governed by its internal structure, its density, temperature, and mass. Now introduce a close binary companion. As that companion swings around the Cepheid on its orbit, its gravitational pull minutely distorts the variable star's shape. When the companion is at its closest approach, its gravity exerts a slightly stronger pull, effectively making it a fraction of a % harder for the Cepheid to expand outward against its own gravity. This acts as a gentle brake on the pulsation. Conversely, when the companion is farthest away, the brake is released. The result is a continuous, tiny speeding up and slowing down of the pulsation period, an effect known as the light travel time effect. It's as if you were listening to a perfectly tuned orchestra, but the lead violinist is subtly being pulled closer to and farther from the microphone by an invisible string, causing their notes to arrive at your ears at slightly shifted times. But in a septuple system, you don't have just one invisible string, you have 6. The signal becomes a complex symphony of overlapping timing shifts. The Cepheid's pulse is not just being modulated by one companion, it's being simultaneously influenced by the gravitational pulls of several other stars, each on their own unique orbit with a different period and strength. The resulting pattern in the timing of the pulsations is a tangled web of advances and delays. Untangling this web requires sophisticated mathematical models, but the payoff is extraordinary. Each gravitational perturber imprints its own specific signature on the pulsation timing. By meticulously decomposing the complex signal, astronomers can not only confirm the presence of the other stars, but can measure their masses and orbital parameters with a precision that is often impossible with other methods. This technique is so sensitive it can even reveal the presence of otherwise invisible companions, like faint red dwarfs or even black holes, whose gravity still affects the pulsating clock even if they emit no light of their own. This transforms the variable star from a simple distance marker into a supremely sensitive gravitational antenna. The tiny changes in its pulsation amplitude are equally telling. The gravitational tides from nearby stars can slightly squash the pulsating star, affecting how much its surface area changes during each cycle and thus how much its brightness varies. By analyzing both the timing and the amplitude of these strange pulsation patterns, astronomers gain a direct dynamical measure of the gravitational forces at play. It's a method that peers deep into the heart of the system's hierarchy, allowing scientists to weigh each stellar component with unprecedented accuracy and map their intricate orbits, all by carefully listening to the nuanced, gravitationally altered heartbeat of a single star. While we have pieced together the nature of the few known septuple systems through decades of painstaking observation, we are standing on the brink of a revolution that will transform this field from a study of rare curiosities into a full-fledged branch of statistical astronomy. This seismic shift is being driven by one of the most ambitious mapping projects in the history of science, the European Space Agency's Gaia mission. Unlike a telescope that stares deeply at a single object, Gaia is a celestial surveyor on an unprecedented scale. Its mission is astrometric, meaning it is designed to precisely measure the positions, distances, and motions of over 1 billion stars in our galaxy with micro-arcsecond accuracy. To put that precision in perspective, it's like being able to measure the diameter of a human hair from 1,000 kilometers away. This relentless, all-sky census is creating a multidimensional movie of the Milky Way, revealing not just where stars are, but how they are moving through space. For the hunt for septuple systems, this data is nothing short of transformative. The traditional method of discovery has been akin to finding a needle in a haystack by carefully inspecting one piece of straw at a time. Astronomers had to suspect a star was interesting based on its strange light variations, then dedicate enormous amounts of telescope time to collect the radial velocity and eclipse data needed to confirm its complex nature. It was a slow, candidate-by-candidate process. Gaia turns this approach on its head. It is effectively imaging the entire haystack at once, with a resolution so sharp that the subtle wobbles of stars are visible directly. A star in a multiple system doesn't travel through space in a perfectly straight line. It pirouettes around the system's common center of mass. Gaia's exquisite measurements of a star's path across the sky, its proper motion, can detect these tiny dances. Even for a septuple system so distant that its stars appear as one point of light to other telescopes, Gaia can see that single point tracing a complex, wobbly path through the galaxy, a clear sign of hidden gravitational complexity. The initial data releases from Gaia have already caused a sensation, revolutionizing our understanding of binary and triple star populations. The upcoming data releases, with their increased precision and longer observational baselines, are poised to do the same for higher-order multiples. It is almost a statistical certainty that Gaia's vast dataset contains dozens, perhaps even hundreds, of septuple systems that have simply been hiding in plain sight, their complex signatures waiting to be decoded by powerful algorithms. We are likely to see the known population double or triple in the coming years, but the true value lies not in the raw numbers but in the statistical power they will provide. With only a handful of examples, every septuple system is a unique individual. Its properties, the masses of its stars, the shapes of their orbits, their age might be exceptional or typical. We have no way of knowing. But with a sample size of 50 or 100 systems, we can finally begin to see the patterns. This will allow astronomers to answer fundamental questions that are currently pure speculation. What is the most common hierarchical configuration for a septuple system? Is the structure we see in Cassiopeiae the rule, or is it an outlier? How does the distribution of stellar masses within these systems compare to the standard initial mass function? Do they preferentially form in certain regions of the galaxy, like the dense spiral arms or the central bulge? A large, statistically significant sample will reveal the typical septuple system, separating universal formation principles from individual quirks of history. It will allow us to test the flyby perturbation hypothesis directly by seeing if systems with misaligned orbits are as common as those with aligned ones. This flood of data will move us from wondering if something can happen to understanding how often it actually does, marking the transition of this field from fascinating anecdote to robust predictive science. The galaxy's most extravagant stellar families are about to step into the spotlight, and their collective story will rewrite our understanding of how stars are born. Yet for all the power of our telescopes and the cleverness of our mathematical models, we are sometimes faced with a celestial mystery that can only be solved by inferring the existence of something we cannot see at all. This is the fascinating frontier of the unseen component, a situation where the observed dance of the stars makes no sense unless we conclude that a hidden partner is leading them. In a handful of suspected septuple systems, the precise orbital data tells a clear but puzzling story. The gravitational math simply does not add up. When astronomers calculate the combined mass of the 6 visible stars and map their intricate motions, they find a persistent discrepancy. The stars are moving as if they are being tugged by an additional, significant source of gravity, a phantom mass that must be present, yet emits no light for our instruments to detect. It is a classic case of celestial detective work, where the crime scene is a patch of sky and the prime suspect is an invisible celestial body. This gravitational anomaly forces astronomers to consider several compelling possibilities for the identity of this unseen partner. The first and most straightforward candidate is a very faint, low-mass star, such as a cool red dwarf or even a brown dwarf that has cooled into obscurity over billions of years. These stellar underachievers can possess substantial mass while emitting only a feeble glow in the infrared, easily lost in the combined glare of their brilliant siblings. A second, more exotic possibility is a black hole. If one of the original 7 stars was massive enough to end its life in a supernova that left behind a stellar mass black hole, it could now be lurking silently within the system's hierarchy, its immense gravity palpably felt but its presence revealed only by its effect on the orbits of the others. A third and truly mind-bending candidate is a massive planet, a gas giant many times the size of Jupiter, on a wide orbit around the entire stellar cluster. While forming such a planet would be a monumental challenge, its gravitational pull would be just enough to account for the subtle orbital irregularities observed. The method for uncovering this ghost is a testament to the precision of modern astronomy. It relies on tracking minuscule deviations in the expected paths of the visible stars. Imagine carefully plotting the future eclipse timings for a tight binary pair within the system, based on the known gravitational influence of the other 5 stars. Then, as years pass, you observe that the eclipses begin to occur consistently a few seconds early or late. This tiny timing error is the crucial clue. It means that the binary's orbit is itself slowly precessing or rotating in a way that cannot be explained by the gravity of the stars we see. The only explanation is that the entire local group of stars is being gently pulled by the gravity of an additional, massive object on a much wider orbit. By analyzing the pattern of these tiny deviations, the specific rhythm of the delays and advances, astronomers can actually calculate the minimum mass of the hidden object and estimate the size of its orbit, effectively weighing and mapping an invisible body. This search represents one of the most active and thrilling areas of research into these complex systems. Confirming the existence of such a hidden component would have profound implications. If it is a black hole, it would be the first identified within a septuple system, offering a unique laboratory to study how these dark remnants interact with their stellar siblings over cosmic time. If it is a massive planet, it would shatter our understanding of planet formation, proving that worlds can coalesce in the most gravitationally hostile environments imaginable. Each candidate system is now under intense scrutiny, with astronomers using the world's most powerful infrared and radio telescopes to hunt for any faint whisper of radiation that might betray the hidden member's presence. Until that moment of discovery, these unseen components remain as theoretical phantoms, their existence a powerful testament to the fact that even in a system with 7 brilliant suns, the most influential character in the gravitational play might be one that lingers entirely in the shadows. But all that gravitational chaos does more than just reshape orbits and trigger eruptions. It fundamentally alters the very life cycle of the stars themselves. In the serene isolation of our own sun, its fate is sealed from the moment of its birth. It will burn through the hydrogen in its core at a steady, predictable rate for about 10 billion years before swelling into a red giant. In a septuple system, this predictable timeline is thrown out the window. The intense gravitational interactions act as a cosmic clockmaker, one that can either wind a star's life forward at a frantic pace or slow its ticking to a near standstill, all depending on its specific role in the chaotic dance. The most dramatic way a star's life can be extended is through a process of internal rejuvenation driven by tidal forces. For a star locked in a tight binary, the constant gravitational pull from its partner doesn't just distort its outer shape, it stirs the entire stellar interior. Think of a star not as a static ball of gas, but as a layered onion. Hydrogen fusion only occurs in the hot, dense core. Once the hydrogen there is exhausted, the star's life on the main sequence is effectively over. But what if you could bring a fresh supply of hydrogen down to the core? This is exactly what tidal mixing can accomplish. The relentless gravitational tugging creates internal currents and waves that churn the stellar plasma, slowly but surely mixing the pristine, unburned hydrogen from the outer layers down into the fusion furnace at the center. It's like having a built-in stirrer that constantly refuels the engine. For these tidally mixed stars, the main sequence lifespan can be stretched out significantly, perhaps by 20 or even 50%. A star that should have died billions of years ago can be kept shining brightly, appearing artificially youthful compared to its isolated siblings of the same mass. This creates a population of stellar Methuselahs within the system. Their prolonged lives are a direct consequence of their gravitational imprisonment. Yet for another star in the very same system, the outcome can be the exact opposite, a tragically shortened existence. This fate befalls the donors in the unstable mass transfer scenarios we've discussed. A star that ventures too close to a hungry companion faces a grim future. As it begins to evolve and swell, its outer layers, still rich with hydrogen fuel, become gravitationally vulnerable. The companion star acts as a vampire, siphoning off this material. This isn't a gentle process, it's a violent stripping that can remove a substantial fraction of the donor's mass in a relatively short cosmic time. This mass loss has two catastrophic effects. First, it literally strips away the star's future fuel supply, but more profoundly, it dramatically alters the star's internal structure. A star's life is a constant battle between the outward pressure of nuclear fusion and the inward crush of its own gravity. By removing the outer layers, you reduce the gravitational pressure holding the core together. The core, no longer compressed as fiercely, actually loosens up and cools slightly, causing the nuclear fusion reactions to slow down or even change their nature prematurely. The star is forced to skip evolutionary stages, rushing towards its end as a helium-burning star or a white dwarf long before its time. A star that could have lived for 10 billion years might have its life cut short to just a few billion, its potential snuffed out by a greedy stellar neighbor. This creates a bizarre dichotomy within the septuple system, a tale of two stellar lifetimes. In one corner, you have a star whose life is extended by the gentle, internal churning of tidal forces. In another, a star is being rapidly dismantled, its lifespan brutally truncated. This means that within a single family of stars, all born from the same cloud at the same time, you can have members existing in radically different stages of evolution. One star might be a steady, middle-aged main sequence star, while its twin, having lost mass, is already a dying red giant, and a third, having been tidally mixed, remains a vibrant youth. The system becomes a living museum of stellar evolution, but one where the exhibits are not arranged by age, but by the chaotic gravitational history each star has endured. This profound alteration of stellar lifespans is perhaps the ultimate testament to the power of a septuple environment. It doesn't just dictate how stars move, but how long they get to live. But the light we see from these systems is only part of the story. To uncover their deepest secrets, astronomers must also listen to the heat they radiate, and this has led to one of the most puzzling discoveries, a strange and persistent infrared excess. When scientists point infrared telescopes toward a septuple star system, they often detect far more warmth than the combined light of the 7 stars can explain. It's as if you pointed a thermal camera at a group of people and found them to be surrounded by a massive, invisible bonfire. This surplus of infrared radiation is the unmistakable signature of warm dust, countless microscopic particles, heated by the starlight until they glow with a faint thermal warmth. The presence of this dust isn't the surprise, it's the sheer amount of it and its likely origins that are so baffling. In a young, forming planetary system, dust is everywhere, the primordial building material for planets. But over time, this dust should clear out. Radiation pressure from the stars and the gravitational sweep of forming planets conspire to either blow the fine dust away or gather it into larger bodies. In a mature system like our own solar system, which is over 4.5 billion years old, the amount of warm, fine dust is negligible. Finding a colossal amount of it in an equally ancient septuple system suggests that something is continuously generating new dust, a process of cosmic destruction that is operating on a scale we can barely imagine. This points to an environment of relentless violence. One leading explanation is a perpetual asteroid belt collision zone of unimaginable proportions. In our solar system, the asteroid belt between Mars and Jupiter is a relatively peaceful place with occasional collisions. But in the chaotic gravitational field of a septuple system, the perturbations from multiple stars would stir up any similar belt into a frenzied state. Asteroids and planetesimals would be on collision courses constantly, slamming into each other at high speeds. Each impact would pulverize the rocky bodies into fine dust, creating a continuous cloud of debris that is then heated by the starlight. The infrared excess we see could be the thermal glow from this everlasting demolition derby, a cloud of pulverized rock so vast it could contain the mass of entire planets ground down to powder over billions of years. An even more dramatic possibility is that we are witnessing the aftermath of a cataclysmic planetary disruption. The unstable orbits within the system make it a place where a planet, even a giant one, could not survive for long in a stable path. A gravitational kick from a passing stellar companion could send a Neptune-sized world careening inward, onto a path that crosses the orbits of other planets or brings it dangerously close to one of the central stars. The resulting collision or tidal disruption would be an event of staggering violence, shattering the planet into a colossal cloud of vaporized rock and dust. The infrared excess would then be the cooling embers of this planetary catastrophe, a ghostly remnant that could take millions of years to fully dissipate. In such a system, these planet-smashing events might not even be rare, but could occur in a cyclical fashion, ensuring a permanent, warm dust supply that makes the system shine brightly in the infrared. The most intriguing source, however, harkens back to the system's violent birth. It's possible that the intense gravitational tides from the 7 stars prevented the protoplanetary disks from ever coalescing into planets in the first place. Instead of forming orderly worlds, the primordial material in the inner system may have been locked in a permanent state of turmoil, with planetesimals constantly being torn apart by stellar encounters before they could grow. The infrared excess we see today could therefore be the direct descendant of that primordial disk, a vast, warped, and puffed-up shroud of dust that has been dynamically stirred and kept from settling for the entire life of the system. This would make the septuple system not just a graveyard for planets, but a place where planets were never allowed to be born, their basic building blocks perpetually held in a state of chaotic suspension, glowing with the combined heat of their 7 suns. And just as stars can be flung from the system, so too could entire worlds be subjected to the same chaotic gravitational forces. This leads us to a wild theoretical possibility that redefines the very notion of planetary orbit, the concept of a slingshot planet. Forget the idea of a world serenely circling a single star. Imagine a planet that becomes a cosmic nomad, using the gravity of multiple suns as a series of interplanetary trampolines. In the frantic core of a septuple system, a planet forming around one star could be subjected to a gravitational slingshot maneuver by another passing stellar member, ripping it from its stable cradle and sending it on a wild, unpredictable journey through the heart of the stellar family. It might swing perilously close to one star, only to be flung toward another, its path a chaotic trajectory governed by the ever-shifting balance of gravitational power. The mechanics behind this are a scaled-up version of the gravity assists we use for our own space probes. A spacecraft will dip close to a planet like Jupiter, stealing a tiny amount of its orbital energy to boost its own speed. In a septuple system, the planets are the probes and the stars are the celestial giants providing the push. The key ingredient is the system's inherent instability over vast timescales. While the hierarchical structure provides general stability, the orbits within it are not perfectly static. They slowly process and evolve, and over millions of years, the delicate gravitational spheres of influence around each star can begin to overlap. A planet on a wide, stable orbit around one binary pair might find its path slowly changing until it makes a dangerously close pass by a star from a different binary group. In that moment, the planet is no longer just orbiting its parent star. It's engaging in a high-stakes gravitational duel with a second massive body. The outcome of this encounter is a cosmic lottery. The planet could receive a gravitational kick that sends it careening inward on a scorching path toward the central stars or outward toward the cold depths of the outer system. It might gain so much energy that it achieves escape velocity, becoming a true rogue planet, ejected from the system entirely to wander the interstellar void alone. But the most fascinating possibility is that the planet isn't ejected but captured. After its wild slingshot ride, the planet's new trajectory could coincidentally align with the gravitational well of a different star within the septuple system. If it loses just enough energy during the encounter, perhaps through a complex interaction with a protoplanetary disk or the gentle tug of another planet, it can be captured into a new, stable orbit around a completely different sun. This planet would become a roving world, a permanent traveler that began its life in one stellar neighborhood and now resides in another, its very existence a testament to a past era of gravitational turmoil. The implications for such a world are staggering. It would be a planet with a split heritage. Its core composition and basic structure would reflect the conditions of the protoplanetary disk where it was born. But its surface and atmosphere would tell a second story, shaped by the light and radiation of its new stellar host. If the planet were slingshotted from the cold outer regions of one star into the warm habitable zone of another, it could experience a sudden, dramatic global thaw. Frozen oceans of water and ammonia could melt, creating a temporary window for life to emerge under the light of a new sun. Conversely, a world migrating inward from a habitable zone to a scorching hot orbit would see its oceans boil away, its atmosphere stripped by intense stellar winds, becoming a ghost of its former self. This dynamicism suggests that in a septuple system, a planet's potential for life is not a permanent state, but a phase that can be violently triggered or extinguished by a random gravitational encounter millions of years in the making. This idea of a star system being a cosmic clock, its rhythm altered by unseen forces, invites us to look back through time with a different kind of instrument, not a telescope, but the historical record itself. It's a captivating thought that some of these septuple systems are not faint, distant specks, but are actually bright enough to be seen without any optical aid at all. The system we've discussed so much, Cassiopeiae, is a perfect example, shining prominently in the northern sky within the familiar W-shaped constellation. For thousands of years, human eyes have gazed upon it, unaware that the single point of light they perceived was in fact a breathtaking gravitational ballet of 7 stars. This raises a tantalizing question. Could ancient astronomers, with their meticulous records of the heavens, have inadvertently documented the first clues to its true nature? The challenge in searching these historical texts is that the variability of a system like Cassiopeiae is subtle and complex. It doesn't flicker dramatically like a dying star. Its changes in brightness are a slow, intricate dance caused by partial eclipses and the mutual brightening of its components. To the naked eye, it would simply appear as a steady star. However, cultures with especially rigorous and long-term astronomical traditions might have picked up on minute discrepancies. The Babylonians, for instance, kept detailed diaries of the night sky for centuries, noting planetary positions and any celestial events they deemed significant. While they didn't have the concept of a variable star as we understand it, they were exceptional observers of patterns. A faint, slow dimming over several years, while unlikely to be recorded as an event, might have been noted as the star appearing weak or diminished in certain years compared to its neighbors, a small annotation that would be incredibly meaningful to a modern historian of astronomy. A more promising avenue lies with the ancient Greek astronomers who attempted to catalogue the brightness of stars systematically. The system of magnitudes invented by Hipparchus and later refined by Ptolemy ranked stars from the brightest first magnitude down to the faintest visible to the naked eye, 6th magnitude. Cassiopeiae sits right on the cusp between 3rd and 4th magnitude. The precision of these early catalogues was remarkable for its time, but it was not infallible. A slight discrepancy in the recorded magnitude of a star like this, when compared to its modern value, could be written off as simple error. But what if that error wasn't random? If multiple independent sources from antiquity consistently listed it as a half magnitude brighter or fainter than it appears today, it could point to a genuine long-term change in the system's overall output, perhaps related to a period of enhanced mass transfer or a series of eclipses that happened to coincide with that era of observation. Perhaps the most compelling historical connection isn't to scientific records, but to myth and nomenclature. The constellation Cassiopeiae itself is named after a vain queen from Greek mythology, often depicted as seated on a throne. It's fascinating to consider that Cassiopeiae lies near the central part of the W, a position that could be interpreted as the heart of the queen. Did its subtle, unpredictable variation in brightness, imperceptible on a night-to-night basis but perhaps noticeable over generations, contribute to the star's association with a capricious and boastful ruler? While this is speculative, it highlights how ancient peoples wove the behavior of the heavens into their cultural narratives, potentially encoding observations we are only now able to decrypt with our technology. The idea that the first data point in the story of septuple star systems was recorded not by a satellite, but by an unknown astronomer etching marks onto a clay tablet under the night sky thousands of years ago, adds a profound layer of human connection to this extraordinary cosmic mystery. But as we chart these complex stellar families, we run into a surprisingly human problem. What do we actually call all these stars? With a simple binary system, the solution is straightforward: Alpha Centauri A and B. Add a third star and you get a C. But when you have 7 stars locked in a multi-layered gravitational dance, the standard naming convention quickly spirals into an alphabet soup of confusion. The challenge of labeling each component in a way that is both precise and intuitively reflects its place in the hierarchy has forced astronomers to develop a surprisingly intricate system of formal and informal designations. The foundation is the system used for simpler multiples, which assigns capital letters from the Latin alphabet A, B, C, and so on, typically in order of discovery or sometimes by brightness. In a septuple system, you might start with the brightest component as A, the next as B, and continue until you run out of letters. But this simple a-through-G approach fails to capture the most important aspect of the system, its nested structure. It tells you there are 7 stars, but it says nothing about which stars are gravitationally married to each other in tight binaries, which pairs are orbiting each other, and which star is the distant loner. To address this, astronomers use a hierarchical system that combines uppercase letters, lowercase letters, and sometimes even Roman numerals. Imagine a septuple system where the primary structure is a tight binary pair. These 2 stars are labeled R and AB. The capital A denotes that this binary is the primary component of the entire system. The lowercase a and b designate the individual stars within that binary. Now imagine this R-AB pair is itself in a wide orbit with another binary pair. That second pair is given the capital letter B, and its own components are labeled bar and BB. So now we have a quadruple system, R, AB, bar, BB. This entire group, acting as a single gravitational unit, might then orbit a third binary pair, which becomes component C with its stars Ca and Cb. Finally, the entire assembly of 6 stars could be bound to a 7th, single star, which would be designated simply as component D. The full, formal name for a star in this system could be something like HD 123,456R, a precise but undeniably cumbersome label that instantly tells an expert its exact place in the celestial family tree. This system is brilliantly logical for those who understand it, but it creates a significant barrier for public communication and even for astronomers discussing the system in broad terms. Saying, "We observed a flare on component bar," is perfectly clear in a technical paper, but in a popular science video or article, it forces the audience to constantly refer back to a complex diagram. Because of this, informal nicknames often emerge. A system might be referred to by its catalog number followed by a descriptive phrase like the close inner binary or the wide tertiary companion. Within research teams, stars might even be given playful, temporary names based on their behavior or discovery order, like the troublemaker for a star that causes frequent eclipses or the quiet one for the distant, stable member. This blend of rigid formality and necessary informality highlights the ongoing challenge of translating the universe's inherent complexity into a language we can easily manage. A reminder that our attempts to classify nature are often as layered and intricate as the phenomena we seek to understand. Projecting the ultimate destiny of a septuple star system requires more than just mathematical equations. It demands the creation of a virtual universe inside a supercomputer. Astronomers feed these powerful machines with all the known data, the precise masses, orbital speeds, and distances of each star, and then set the simulation running forward across billions of years. The results are not a single, predetermined movie, but a collection of probabilistic scenarios, each one a glimpse into a possible future filled with cosmic violence and dissolution. The journey begins not with a bang, but with a slow, inevitable drift. Over the first few 100 million years, the system's hierarchical structure provides remarkable stability, but it is not immune to the subtle effects of gravitational radiation and the gentle tugs of passing stars. These tiny perturbations accumulate like grains of sand, slowly shifting the balance of a vast scale. The first major event is almost always the death of the most massive star in the system. In the tight inner binaries where stellar evolution is fastest, a star 20 times heavier than our Sun will live for only a few million years. Its demise is a spectacular supernova, a flash that briefly outshines the entire galaxy. The simulation shows this explosion as a sudden, violent recoil. The instant loss of over 80% of the star's mass sends a gravitational shockwave through the entire system. The remaining stars, their orbits suddenly unmoored from their massive anchor, recoil and shift into new, often more eccentric paths. What was once a stable septet is now a sextet, and the supernova's fury may have even given the entire system a kick, sending it careening through the galaxy as a runaway stellar family. The aftermath of this first supernova leaves behind a neutron star, or, if the original star was massive enough, a stellar mass black hole. This new, dark remnant now becomes a permanent, silent member of the gravitational dance. The simulations reveal that its presence fundamentally alters the system's long-term stability. If the supernova kick was gentle and the remnant remains bound, it continues to orbit its binary partner. However, that partner will itself eventually evolve, swelling into a red giant. This sets the stage for a second act of cosmic vampirism, but now with far higher stakes. The black hole or neutron star begins to pull material from the giant's atmosphere, forming a superheated accretion disk that blasts out X-rays. This process of mass transfer can be stable for a time, but the simulations often show it becoming unstable, leading to dramatic eruptions or even the complete tidal disruption of the giant star. The transfer of mass also changes the binary's orbit, sometimes driving the two objects closer together in a tightening spiral. This is where the true chaos unfolds. The death of the first massive star is rarely an isolated event. It is merely the opening salvo in a chain reaction of stellar demise. The other massive stars in the system, themselves aging on similar timescales, will soon follow suit. The simulations show a sequence of supernova occurring over a span of a few 100 million years. Each explosion further destabilizes the delicate gravitational hierarchy. Stars that were once in stable, wide orbits find their paths distorted by the successive blasts of mass loss and recoil. The system begins to resemble a game of gravitational pinball. The most likely outcome, repeated across thousands of simulation runs, is the progressive ejection of the system's members. A close encounter between three stars, a common occurrence in the now chaotic core, can lead to a gravitational slingshot. One star is flung out of the system entirely, becoming a hypervelocity star racing into the galactic halo. Another supernova might provide just enough of a kick to unbind a wider binary pair, sending them off together as a binary runaway. With each ejection, the system becomes simpler, shedding its complexity until only a tight core remains. The final state of the system depends critically on what is left behind after the era of supernova concludes. One common endpoint is a stable but much simpler multiple system. The simulations might leave behind a tight binary consisting of two white dwarfs, or a white dwarf and a neutron star silently orbiting each other. These pairs will continue to spiral inward over billions of years due to the emission of gravitational waves, eventually merging in a final, brilliant flash. Another possibility is that the system retains its central black hole or neutron star, now orbited by one or two lower mass stars that manage to avoid ejection. This creates a long-lived but quieter, high-energy binary source. In the most extreme simulations where multiple supernovae occur in very tight binaries, the system's core can become a nesting ground for two or even three compact remnants. The gravitational interactions between these ultra-dense objects are so violent that the final outcome is almost always the complete disintegration of the system. The last few stars and black holes are flung in opposite directions, their gravitational bonds severed forever. The ultimate fate, then, is one of cosmic dispersal. The Septuple system, a gravitational masterpiece that endured for billions of years, does not die with a single cataclysm but rather unravels. Its stellar members are scattered across the galaxy, their paths diverging forever. The once-bound family becomes a collection of solitary ghosts, isolated neutron stars, wandering black holes, and lone main sequence stars whose high proper motion is the only clue to their violent origin. The rich debris of pulverized planets and asteroid belts is blown away by stellar winds and radiation pressure, dissipating into the interstellar medium. The heavy elements forged in the hearts of the massive stars and scattered by their supernova become part of the galactic recycling program, eventually enriching future generations of stars and planets. The simulations show that the Septuple system's greatest legacy is not its long life, but its dramatic death, which seeds the galaxy with the building blocks of new worlds and the strange, dark remnants of its own spectacular past. But beyond the gravitational drama and the violent life cycles of their stars, these systems hold a mystery so fundamental it reaches down to the very nature of matter itself. When astronomers direct their most powerful spectroscopes toward the combined light of a septuple system, they occasionally capture a signature that defies all classification. Weaving through the familiar rainbow of starlight are dark absorption lines or bright emission spikes that sit at wavelengths which don't correspond to any element on the periodic table. They are spectral ghosts, lines of light or shadow with no known identity, while the most immediate explanation points to known atoms behaving in radically unfamiliar ways. The persistent presence of these unidentifiable lines forces a moment of thrilling scientific humility, a reminder that even our most complete models of physics might be missing a piece of the cosmic puzzle. To appreciate the mystery, we need to understand how spectroscopy works as a cosmic fingerprinting tool. Every element, when heated or energized, emits or absorbs light at specific, unique wavelengths. Hydrogen has its signature lines, helium has its own, and iron has a complex forest of them. For over a century, astronomers have used these spectral fingerprints to determine the chemical composition of stars, galaxies, and nebulas across the universe. The catalogue of known lines is exhaustive, a map that has allowed us to decode the universe's elemental makeup. So, when a line appears that cannot be matched to this vast library, it creates a profound puzzle. In the context of a septuple system, the mystery deepens because the environment is so extreme. The intense radiation fields from multiple stars can strip atoms down to highly unusual ionization states, creating ions that are difficult or impossible to study in Earth-bound laboratories. A molecule formed in the relative cool of a circumstellar disk might also be subjected to such powerful magnetic fields or pressures that its spectral signature is warped into something unrecognizable. The leading theory, therefore, is that these unidentified lines are not evidence of new physics, but a signature of old physics operating under conditions we can scarcely replicate. However, the most tantalizing possibilities emerge when all conventional explanations are exhausted. Could these lines be the signature of exotic matter, or states of plasma that only exist under such ferocious gravitational and magnetic stress? Some theoreticians have pondered whether the interiors of neutron stars or the accretion disks around black holes within these systems could be creating strange forms of matter like quark-gluon plasma, which might emit a spectral signature we have yet to catalogue. It's a long shot, but it highlights how these complex systems act as natural laboratories for physics at the extreme. The unidentified lines serve as a beacon, pointing toward physical processes that push the boundaries of our current understanding, inviting a new generation of physicists and astronomers to look closer and think deeper about what might be possible in the universe's most chaotic corners. And this intricate puzzle of spectral lines and chaotic evolution leads us to a grander unifying theory, one that connects the existence of these rare septuple systems to the most fundamental process of cosmic construction. The sheer improbability of 7 stars binding together isn't just a random fluke. It appears to be a direct and natural byproduct of the universe's method for building its most massive stellar giants. The key lies in the environment. Truly high-mass stars, those behemoths dozens of times heavier than our Sun, are never born in isolation. They require an exceptionally dense and massive reservoir of gas to coalesce, and such nurseries inevitably give birth not to one star but to entire crowded clusters. It is within these stellar metropolises where newborn suns are packed thousands of times more tightly than in our own neighborhood that the complex gravitational dance necessary for a septuple system becomes not just possible but almost expected. Think of a massive star-forming region like the Orion Nebula, but on an even more colossal scale. As a giant molecular cloud collapses under its own gravity, it doesn't simply fragment into a few large pieces. It undergoes a process of competitive accretion where dozens of smaller cores form simultaneously, all vying for the same surrounding gas. In this frantic scramble, the cores that form in the deepest part of the gravitational well gain a decisive advantage, sucking in material at a ferocious rate and growing into the high-mass stars. But crucially, these nascent stellar embryos are born extremely close together. Their initial velocities are not enough to easily escape each other's gravitational pull, forcing them into a complex web of interactions right from the start. The same immense gravitational potential that feeds the growth of individual massive stars also acts as a glue, binding together a larger number of stellar siblings into a stable, hierarchical family. A septuple system, therefore, is not an anomaly. It is the ultimate expression of star formation in its most extreme, high-density mode. The system itself is a miniature cluster that managed to achieve a stable configuration rather than flying apart. This revelation elevates septuple systems from mere curiosities to indispensable cosmic laboratories. High-mass stellar astrophysics faces a significant challenge. These stars live fast and die young, making them difficult to study in detail. But in a septuple system, we have a unique controlled experiment. We can observe the interactions between stars of different masses, all born from the same cloud at the same time, but evolving at dramatically different rates. The effects of fierce stellar winds from the most massive members on their lower mass siblings, the transfer of material, and the triggering of premature evolutionary stages can all be studied within a single gravitationally bound group. By decoding the complex history written in the orbits and atmospheres of these 7 stars, we gain unparalleled insight into the physics that governs all high-mass stars, from their turbulent birth in dense clusters to their dramatic supernova deaths. These rare gravitational families are, in essence, a master key, unlocking secrets about the most energetic and influential stars in the galaxy, whose short lives profoundly shape the chemical evolution and structure of everything that comes after them. Considering the ultimate fate of a septuple system forces us to look billions of years into the future, to an era when the brilliant main sequence stars we see today have long since burned out. What remains is a ghostly collection of stellar corpses, a celestial graveyard that is anything but quiet. The complex gravitational ballet that defined the system's youth becomes, in its old age, a dance of the dead. The end states of stellar evolution are compact objects, white dwarfs, neutron stars, and black holes, and in a system that began with 7 stars, the potential combinations are staggering. We are left with the extraordinary possibility of a system hosting not just one, but multiple binary pairs of these incredibly dense remnants. Imagine a tight binary of 2 white dwarfs, the Earth-sized cores of expired suns whirling around each other. This pair could itself be orbiting a binary system of neutron stars, city-sized objects more massive than our Sun. And this entire quartet of dead stars might be gravitationally bound to a final pair, perhaps a black hole and its white dwarf companion. This creates a zoo of compact object binaries, a menagerie of gravitational powerhouses contained within a single, intricate system. The significance of this goes far beyond mere celestial curiosity. Each of these binary pairs is a potent source of gravitational waves. According to Einstein's theory of general relativity, any massive object in accelerated motion ripples the fabric of spacetime itself. A pair of white dwarfs or neutron stars in a close orbit are perpetually accelerating as they spin around each other, continuously radiating energy away in the form of these faint, invisible ripples. In a simpler, isolated binary, this process is steady and predictable. But in the crowded environment of our evolved septuple system, the gravitational waves emitted would be a complex symphony of overlapping signals. The inspiral of the white dwarf binary would produce waves of one frequency, while the tighter, faster neutron star binary would emit waves of a much higher pitch. Advanced gravitational wave observatories of the future, sensitive to a broader range of frequencies than our current detectors, would hear this system as a distinctive chord in the cosmic background hum, a direct sound from a graveyard of stars. The most dramatic possibility, however, involves the neutron star binaries. As they spiral closer together over billions of years, losing energy to gravitational waves, their fate is sealed. If two neutron stars come too close, they will collide. This event, known as a kilonova, is one of the most cataclysmic and fruitful processes in the universe. The collision unleashes a blinding flash of gamma rays and a brilliant optical afterglow that can outshine an entire galaxy for a few days. But the true legacy of a kilonova is what it creates. The immense pressures and temperatures of the collision are a cosmic forge, producing staggering amounts of heavy elements like gold, platinum, and uranium. A single kilonova event can manufacture hundreds of Earth masses worth of gold, scattering these precious metals into the surrounding space to be incorporated into future generations of stars and planets. Now consider the implications within our Septuple system. If it contains multiple neutron star binaries, it becomes a potential factory for not just one, but a series of kilonova events spaced out over cosmic time. The first collision would seed the entire system with a rich supply of heavy elements. Any remaining gas or even planets orbiting the other stars would be suddenly enriched with these newly forged materials. Then, millions or billions of years later, a second neutron star pair might merge, repeating the process. This turns the system into a recurring engine of cosmic nucleosynthesis, a place where the universe's supply of heavy elements is built up in successive waves. The presence of other compact objects like black holes adds another layer of complexity. A close pass from a black hole binary could dynamically perturb a neutron star pair, hurling them toward each other and triggering a premature merger that might not have occurred for many more billions of years otherwise. The Septuple system, in its final act, transforms from a cradle of stars into a crucible of creation. Its violent death throws responsible for seeding the cosmos with the very elements that make worlds like ours and life itself possible. But to truly understand the heart of these stars, we must learn to listen to their music. Beyond the eclipses and the spectral lines, each star in a Septuple system has its own unique rhythm, a subtle, constant vibration that pulses through its interior. This field of study is known as astroseismology, and it allows astronomers to perform a kind of cosmic ultrasound, using a star's natural oscillations to see deep inside its structure. Just as geologists use seismic waves from earthquakes to map Earth's core, astronomers use the flickering brightness of a star caused by sound waves trapped within its gaseous body. These waves race through the stellar interior, bouncing between the core and the surface, and their behavior is exquisitely sensitive to the star's density, temperature, and rotation. In a solitary star, this creates a regular, predictable pattern of pulsations, a steady hum that reveals its internal conditions. However, place that same star into the gravitational whirlwind of a Septuple system, and its song becomes something far more complex and revealing. The gravitational tides from the star's multiple companions act as a constant, external tampering force on these delicate internal vibrations. Imagine a perfectly tuned bell ringing with a clear, pure tone. Now imagine gently placing your hand on the bell's surface. As it rings, the tone changes, becoming slightly distorted. This is precisely what happens to the pulsations of a star in a tight binary pair. The gravitational pull of its close partner subtly distorts the star's spherical shape, altering the pathways and frequencies of the sound waves traveling within it. The regular pulsation pattern becomes split into multiple, closely spaced frequencies, a phenomenon akin to a musical chord. By meticulously measuring this chord, scientists can determine the strength of the tidal forces, which in turn tells them the mass of the perturbing companion with incredible precision. It's a method so sensitive it can even reveal the presence of a low-mass star or a large planet that would otherwise be invisible, its existence betrayed only by the subtle distortion it imposes on its host star's internal music. This goes far beyond simply detecting hidden objects. The oscillations provide a direct window into the star's internal rotation. In our Sun, the equator rotates faster than the poles, a phenomenon known as differential rotation. In a septuple system, the intense tidal locking can dramatically alter this internal spin. Astroseismology can measure whether the star is rotating as a solid body or if its different layers are shearing against one another. The data suggests that in these extreme environments, the tidal forces can enforce a state of near-rigid rotation, effectively spinning the entire star like a ball from its core to its surface. This has profound implications for the star's magnetic field, which is generated by the churning motion of plasma in its interior. A change in the internal rotation profile can amplify or suppress the magnetic dynamo, leading to the incredibly powerful and tangled magnetic fields we discussed earlier. By decoding the pulsations, astronomers can essentially map the star's inner dynamics, understanding how the external gravitational chaos is directly shaping the internal engine. Perhaps the most powerful application of this technique is in weighing and measuring the stars with unparalleled accuracy. The frequency of a star's fundamental pulsations is directly tied to its average density. A dense, compact star will pulsate rapidly with a high-pitched rhythm, while a large, bloated giant will pulse with a slow, deep beat. In a septuple system where the stars are all born together, astroseismology provides a way to weigh each member independently. By measuring the pulsations of one star, astronomers can calculate its density and, knowing its size from other observations, determine its mass. This creates a benchmark that can be used to test and refine the orbital models derived from radial velocity measurements. It's a cross-check of cosmic proportions, ensuring that our understanding of the system's gravitational dance is built on a foundation of solid, internal data rather than inferred motions. This allows for the creation of a precise mass ledger for all 7 stars, a critical piece of information for modeling the system's formation, stability, and ultimate fate. The gentle, rhythmic pulsations of these distant suns, once decoded, provide the most detailed autopsy report imaginable, laying bare the secrets of their birth, their structure, and the powerful external forces that dictate their lives. To understand the origin of a septuple star system, we must journey back in time to its cosmic nursery, a place far removed from the serene emptiness of interstellar space. These stellar families are not born in just any cloud of gas and dust. They emerge from the most extreme, violent, and densely packed molecular clouds in the entire galaxy. Think of a typical stellar nursery like the Orion Nebula, a beautiful and active region, but then compress it 1,000-fold, amplifying its internal turbulence to a fever pitch. The molecular clouds that give rise to septuple systems are the ultimate cosmic incubators, possessing a specific and rare combination of properties that makes the simultaneous birth of 7 stars not just possible but almost inevitable. The key ingredients are immense density and a particular kind of controlled chaos. These clouds are not homogeneous blobs. They are fractal landscapes of nested filaments and dense knots, structures within structures, all on the verge of gravitational collapse. It is within these ultra-dense knots, where the gas is packed so tightly that light years of material are squeezed into a region just a few times larger than our solar system, that the magic, or rather the physics, happens. The process begins with a delicate balance between forces. The cloud is supported against its own gravity by a combination of internal gas pressure, magnetic fields, and most importantly, turbulence. This turbulence is the random, supersonic motion of the gas, creating a swirling, chaotic environment. In a typical cloud, this turbulence is enough to prevent widespread collapse, allowing only a few isolated cores to form. But in the progenitor clouds of septuple systems, the turbulence operates on a different level. It's not just chaotic, it's structured in a way that actually promotes fragmentation. Imagine a pot of vigorously boiling water. The churning motion doesn't just prevent things from forming, it can create a multitude of bubbles. Similarly, the supersonic turbulence in these special clouds creates a complex web of intersecting shock waves. Where these shock waves collide, they compress the gas to incredible densities, creating not one or two, but dozens of potential sites for star formation, all nestled incredibly close together. This leads to the critical phenomenon of competitive accretion, a frantic scramble for material that dictates the final masses of the stars. In this crowded, high-stakes environment, the multiple cores that form are not born in isolation. They all vie for gas from the same surrounding reservoir. The cores that form in the deepest part of the overall gravitational well, or that start out with a slight mass advantage, become gravitational vacuums. They hoard the infalling gas, growing rapidly into the high-mass stars of the system. Meanwhile, the weaker, smaller cores are starved, destined to become the lower-mass red dwarfs. This process naturally explains the strange mass distributions we sometimes see, with a few heavyweights and a cluster of lightweights, but a gap in the middle. The intermediate mass cores lost the gravitational tug of war. The entire system is born in a single, rapid, and violent burst of creation, with the hierarchical structure, the tight binaries and wider pairs, imprinted from the very beginning by the specific geometry of the collapsing cloud fragments. The stable septuple system we observe billions of years later is not the product of a slow assembly. It is the rare survivor of a frenzied and ultra-dense birth, a gravitational masterpiece forged in the most extreme furnace the galaxy has to offer. To truly grasp the mind-bending architecture of a septuple star system, it helps to start with a cosmic landmark that many amateur astronomers know and love: the star system Epsilon Lyrae. If you've ever pointed a small telescope toward the constellation Lyra near the brilliant Vega, you may have noticed a fascinating sight. To the naked eye, it appears as a single star. But through binoculars, it splits into two. Now aim a more powerful telescope at each of those 2 points of light, and you'll witness something magical. Each one of them resolves into a pair of stars. You are not looking at a double star, but at 2 double stars orbiting each other. This is why Epsilon Lyrae earned the perfect nickname, the double-double. It's a stunning, real-world example of a hierarchical quadruple system, a pair of pairs, a beautiful demonstration of celestial organization. Now, let's take that concept and push it to its logical and truly extreme conclusion. Imagine a double-double-double. Visualize 2 separate double-double systems, each one a stable quartet of stars with its own intricate dance. Now, picture these 2 quadruple systems themselves engaged in a slow, stately orbit around each other. That would give you an octuple system, 8 stars in a breathtakingly complex arrangement, but we're searching for a septuple, a system of 7. So let's adjust our imaginary model. Instead of 2 full quadruple systems, imagine one double-double, that's 4 stars. Then add another binary pair that brings our total to 6. Finally, add a single 7th star that orbits the entire central cluster of 6 from a great distance. What we've just built in our minds is a double-double plus a double plus 1. This layered analogy is the key to understanding the gravitational sanity of a system like Cassiopeiae. The profound importance of this structure is that it provides the stability needed for such a complex family to survive for billions of years. A system with 7 stars all buzzing around a single point would be a gravitational disaster, flinging members into the void in a cosmic instant. The hierarchical model prevents this chaos by creating what astronomers call a separation of scales. The stars in the tightest inner binaries are so preoccupied with their immediate partners, whirling around each other in a matter of days, that they are almost completely oblivious to the gentler gravitational nudges from the stars in the wider orbits. It's like being in a lively, noisy conversation at a crowded party. You're intensely focused on the person you're talking to, and the general din of the room becomes a distant background hum. The gravitational noise from the outer stars is simply too faint and slow to disrupt the frantic dance of the inner pairs. This analogy also helps us understand the incredible timescales involved. The innermost binary might complete an orbit in a week. The orbit of that pair around its companion binary could take a year. The dance of that quartet with the wider binary pair might unfold over a century. And the grand orbit of the seventh star around the entire assembly could span millennia. Each level of the hierarchy operates on its own clock, largely independent of the others. This is why these systems can be ancient. The violent interactions are localized and contained. The double plus one model isn't just a helpful visual. It's a reflection of the fundamental physics that allows such extravagant stellar families to exist, offering a relatable framework for one of the most complex gravitational puzzles in the known universe. Yet even with all these intricate orbital dances and gravitational assists, the sheer density of stars in the inner sanctum of a septuple system introduces a possibility that is both terrifying and spectacularly creative: the chance of a direct head-on collision. In the vast emptiness of space, such an event is almost unthinkably rare. But in the crowded core of this stellar family, where several suns are separated by distances comparable to the span of our own solar system, the unthinkable becomes statistically plausible over billions of years. The trigger is often a subtle, long-term gravitational perturbation. The gentle but persistent tugs from the wider stellar companions can slowly torque the orbits of an inner binary pair, driving their paths to become more and more eccentric over millennia. What was once a safe, circular orbit can gradually stretch into a long, narrow ellipse, a trajectory that brings the two stars perilously close at their point of closest approach, or periastron. With each orbit, the risk grows until finally, on one fateful pass, the stars do not swing by each other, they meet. The result is not a titanic explosion, as one might imagine, but something more like a violent and beautiful merger. The two stars, each a colossal ball of incandescent plasma, slam into one another at speeds of hundreds of kilometers per second. Their outer atmospheres are instantly shredded, forming a hot, common envelope of gas that temporarily engulfs both stellar cores. Inside this shroud, the cores spiral inward, their orbits decaying due to friction with the surrounding material. Over a period that is brief in cosmic terms, perhaps only a few thousand years, the two cores finally coalesce into a single new star. The energy released in this merger is staggering, causing the new object to blaze with an intensity that can outshine the rest of the system combined for a short period. What emerges from this cosmic wreck is a stellar phoenix, an object known as a blue straggler. This newly formed star is a true anomaly. It appears mysteriously young, hot, and blue, standing out brilliantly against its stellar siblings. The reason is a complete rejuvenation. The merger violently stirs the interior of the new star, funneling a massive fresh supply of hydrogen from the outer layers down into the core. This restokes the furnace of nuclear fusion, making the star burn hotter and brighter than either of its progenitors ever did. It's as if two middle-aged stars combine to create a brilliant teenager, effectively resetting their evolutionary clock. This blue straggler now has a new lease on life, potentially shining for billions of years longer than it would have otherwise. But its creation comes at a cost to the system's complex identity. The star count has been permanently reduced. The intricate gravitational balance is suddenly altered as the mass of two stars is now concentrated into one. The system must reconfigure itself, adjusting orbits and relationships to accommodate this new, more massive gravitational anchor. A septuple system might, in a single cataclysmic event, become a sextuple, a dramatic simplification born from the most chaotic interaction imaginable. But to truly map the gravitational labyrinth of a septuple system, we need a clock of unparalleled precision, something that makes the most accurate atomic timekeepers on Earth seem primitive. Fortunately, the universe provides its own perfect chronometer in the form of a pulsar. Imagine the collapsed core of a massive star, a neutron star spinning hundreds of times per second. As it rotates, it beams radiation from its magnetic poles like a cosmic lighthouse. If one of those beams sweeps across our line of sight, we detect a pulse of radio waves with a regularity that rivals and often surpasses anything humanity can build. This is the heartbeat of a pulsar, and its steady rhythm offers a tool of exquisite sensitivity for probing the most complex gravitational fields. The concept of a pulsar timing array takes this a step further. Instead of relying on a single clock, astronomers monitor a network of these cosmic lighthouses across the galaxy, creating a galaxy-spanning web of precision timing. The slight correlated delays in their pulses can reveal the passage of low-frequency gravitational waves, but on the scale of a single system, the timing of just one pulsar can reveal the intricate dance of its stellar companions with breathtaking detail. The principle is elegantly simple. If a pulsar is in a simple orbit with one companion, its pulse arrival times will vary in a smooth, predictable pattern. As the pulsar moves towards us in its orbit, the pulses arrive slightly more frequently. As it moves away, they are spaced slightly farther apart. This creates a clean, repeating sinusoidal wave in the timing data. Now introduce a second gravitational influence. The pulsar's orbit is no longer a simple ellipse around a single point. The gravitational pull of the second star causes the entire orbit to wobble or precess in a complex way. This adds a second, slower rhythm to the timing variations, a subtle modulation layered on top of the first. In a septuple system, this process is amplified to an extreme. The pulsar is not being tugged by one or two companions, but by 6 other massive bodies, each on its own unique orbit. Its path through space becomes a convoluted, ever-changing trajectory. The clean timing signal transforms into a chaotic tapestry of overlapping advances and delays. The pulse doesn't just arrive early or late, it stutters and jitters in a pattern that is the direct fingerprint of the system's immense gravitational complexity. Untangling this signal is a monumental computational challenge, but the payoff is a complete gravitational map of the system. Each stellar companion imprints its own specific signature on the pulsar's timing delays, a signature defined by its mass and orbital parameters. By using supercomputers to run millions of simulations, testing different combinations of masses and orbits, astronomers can find the one unique model that perfectly reproduces the observed chaotic timing pattern. This method is so powerful that it can reveal the presence of otherwise invisible components. A faint, dark object like a white dwarf or even a black hole, which emits no light of its own, still exerts a gravitational pull. Its mass will cause a distinct, recurring anomaly in the pulsar's timing, betraying its existence with unerring certainty. A pulsar timing array within a septuple system thus becomes the ultimate gravitational detector, capable of weighing every single member of the family, both seen and unseen, and plotting their precise paths through the cosmic void. It is the smoking gun that confirms not just the number of stars, but the full, dynamic architecture of their perpetual dance. But the story of these stellar families extends far beyond their own intricate dances. They hold within them a deep and ancient memory of the galaxy itself. Every star is a time capsule, its chemical makeup a permanent record of the specific ingredients present in the cloud of gas and dust from which it was born. For most stars, this record is like a single, faded photograph from their infancy. But a septuple system is something far richer. It's a complete family portrait from a specific era in the galaxy's history, offering a multifaceted glimpse into conditions that have long since vanished. This transforms them into powerful tools for a field known as galactic archaeology, where astronomers act as cosmic historians, using the stars to piece together the Milky Way's turbulent past. The key lies in the concept of metallicity, which is the amount of elements heavier than hydrogen and helium that a star contains. These heavier elements, which astronomers collectively call metals, were not present in the early universe. They were forged in the nuclear furnaces of massive stars and then scattered across space in violent supernova explosions. Each successive generation of stars is born from gas that has been enriched by the ashes of its predecessors. This means that a star's metallicity is a direct indicator of its age. A star with very low metallicity, like a pristine relic from the dawn of time, must be extremely old. A star with high metallicity, like our Sun, was born more recently from well-polluted gas. Now, apply this to a septuple system. Because all 7 stars formed from the same primordial cloud at the same time, they should all share an identical initial metallicity. They are a chemically homogeneous family, a snapshot of the interstellar medium in one particular location at one specific moment billions of years ago. By measuring the metallicity of just one member, we can effectively date the entire system and, by extension, learn about the chemical environment of that particular region of the galaxy when it was young. Finding a septuple system with very low metallicity would be like discovering a living fossil, a group of stars that formed when the Milky Way was just a primitive disk still assembling itself. Their orbits would also be a clue. They might follow a path that is very different from the orderly circular orbits of younger stars in the galactic disk, hinting at a more chaotic and violent epoch in the galaxy's formation. However, as we've seen, the simple story is often complicated by the system's own internal drama. The same mass transfer events that create blue stragglers and alter stellar lifespans also contaminate the pristine chemical record. A star that has absorbed material from an evolved companion will have its surface metallicity artificially inflated, its original birth signature overwritten by a later event. This is where the forensic power of studying all 7 stars becomes critical. By comparing the chemical abundances of each member, astronomers can identify which stars have been polluted and which have retained their original composition. The star that has been a recipient in a mass transfer event will stand out with abnormally high levels of carbon or nitrogen, while a star that has orbited peacefully on the outskirts of the system might still hold the pure, unaltered signature of their common birth. This allows scientists to perform a kind of cosmic restoration. They can subtract the effects of the later pollution to peer back at the original chemical recipe. When they do this, they find that many septuple systems have a metallicity that is surprisingly high for their estimated age based on their orbital dynamics. This suggests that they formed not in the pristine outer halo of the galaxy, but within the more rapidly enriching environment of the galactic disk, possibly even in a spiral arm that has since wound itself into a different configuration. Their current location and motion can then be traced backwards, revealing their migration path across the galaxy over billions of years. Each septuple system is therefore a unique data point, a fossilized bubble of the early galactic disk whose chemical composition and space motion tell a story about the conditions and dynamics of the Milky Way at a specific chapter in its multi-billion-year history. They are not just celestial wonders, they are Rosetta Stones for deciphering the evolution of our cosmic home. We've explored the incredible stability of hierarchical orbits and the precise choreography that allows these 7 star families to endure, but this apparent order masks a deeper, more fundamental truth about the universe itself. The gravitational dance of any multiple star system runs headlong into one of the most infamous problems in all of physics, a mathematical puzzle so complex it has been deemed fundamentally unsolvable for more than 3 centuries, the n-body problem. In a system with just 2 stars, Newton's laws provide a perfect, elegant solution. Their orbits are stable, predictable ellipses, and we can calculate their positions with perfect accuracy millions of years into the future or the past. The moment you introduce a third gravitating body, everything changes. There is no neat, closed-form equation that can precisely describe the long-term motions of three stars under their mutual gravity. The system becomes chaotic, meaning that even the tiniest, most imperceptible change in the starting conditions, a difference in position less than the width of an atom, will lead to wildly divergent outcomes over a long enough time. This is the notorious three-body problem, the bane of astronomers and physicists since Newton's time. Now take that inherent, profound chaos and amplify it to an almost unimaginable degree. A septuple system is not a three-body problem, it is a seven-body problem. It is the three-body problem on astronomical steroids. While the hierarchical structure we've discussed provides a kind of temporary scaffolding that suppresses the most violent instabilities, it does not eliminate the underlying mathematical reality. The system is, at its heart, chaotic. This means that while we can create incredibly sophisticated computer models that simulate the system's behavior for thousands or even millions of years, there is an absolute limit to our predictive power. We can never know the exact positions of all 7 stars 10 million years from now. The equations of motion for 7 interacting bodies are so sensitive to their initial conditions that any prediction eventually diverges from reality. The system's fate is not written in stone, it is written in probabilities. This forces a profound shift in how we must study these cosmic families. We abandon the dream of deterministic prediction, knowing exactly what will happen, and embrace a statistical approach. Instead of running one simulation, astronomers run thousands, even millions of them. In each run, they slightly tweak the starting positions and velocities of the stars within the range of our observational uncertainty. They then let the virtual clock run forward and watch what unfolds. In some simulations, the system remains stable for billions of years. In others, a close pass leads to a stellar ejection within a few million years. In a few, a catastrophic collision occurs. The result is not a single story, but a distribution of possible futures. We can say, for example, that there is a 95% probability the system will remain bound for the next 100 million years, a 4% chance it will eject one star, and a 1% chance of a direct collision. This statistical cloud of possibilities is the only truthful way to describe the long-term destiny of a septuple star system. It is a universe not of certainty, but of likelihoods, a reminder that even in the clockwork motions of the heavens, there lies an irreducible element of chaos. While the immense computational power of supercomputers and the sharp optics of space telescopes are vital, there is another, deeply human force that has become indispensable in the study of these complex systems: the global community of amateur astronomers and citizen scientists. In an era where professional observatories are often oversubscribed, with time allocated in precious, short bursts, the patient, persistent gaze of dedicated hobbyists from their backyards around the world is providing a continuous stream of data that is simply impossible to gather any other way. The key to unlocking the secrets of a septuple system lies in its light curve, the long-term record of its brightness fluctuations. And capturing the full, intricate story of that light curve requires nightly observations, year after year, a task perfectly suited to the passion and dedication of the amateur community. The contribution is focused on a technique called photometry, which is the precise measurement of a star's brightness. For a target like Cassiopeiae, the goal is not to take a beautiful picture, but to obtain a single, crucial number each night, its exact magnitude. Using equipment that is surprisingly sophisticated, often comprising telescopes, specialized cameras, and software available to serious enthusiasts, these observers meticulously capture the star's light. They then compare it to the brightness of known, stable comparison stars in the same field of view. cancelling out the effects of the Earth's atmosphere to derive a measurement of astonishing accuracy. Night after night, in backyards and on balconies, they add another date to point to a light curve that stretches back for decades. This long baseline is the gold standard. It is this patient accumulation of data that reveals the subtle, long-term changes in the system, such as the slow brightening or dimming that might indicate a period of increased mass transfer or the gradual precession of an orbit. One of the most powerful aspects of this collaboration is its ability to catch the unexpected. Professional telescopes might observe a system like this for a few nights every 6 months, creating a series of snapshots. But what if a sudden, brief flare occurs, or a series of complex, overlapping eclipses happens during the gaps in that schedule? It would be missed entirely. Citizen scientists, with their constant monitoring, act as the universe's watchdogs. There are documented cases where an amateur astronomer, routinely checking their data, has noticed a strange, short-lived dip in a star's brightness that wasn't there the night before. They quickly alert the professional community, often via organizations like the American Association of Variable Star Observers, or AVSO. This alert can trigger a rapid response from professional observatories, which then turn their powerful instruments toward the target to catch the tail end of the event, obtaining high-resolution spectra or X-ray data that would have been impossible without that initial tip-off. In this way, the amateur is the one who rings the alarm, turning the entire astronomical community's attention to a fleeting moment of cosmic drama. The impact of this work extends far beyond individual discoveries. It is fundamentally a story of partnership. Professional astronomers simply do not have the resources to monitor hundreds of candidate systems with the required nightly frequency. By empowering a global network of observers, the scientific community can effectively keep a continuous eye on dozens of intriguing targets simultaneously. Data from thousands of observations made by amateurs are uploaded to public archives, where they are freely available for anyone to analyze. This vast, crowdsourced dataset allows professional researchers to test their complex models of hierarchical orbits against real-world observations spanning many years. When a model predicts a subtle change in the timing of an eclipse that will occur over the next decade, it is the dedicated amateur astronomer who will be there to check if the prediction holds true. This synergy between the patient, wide-scale monitoring of citizen scientists and the targeted, deep analysis power of professional institutions is creating a new paradigm for doing astronomy, one where discovery is a truly collaborative endeavor that spans the globe. And so we reach the final and perhaps most profound of our 50 discoveries. After this journey through gravitational chaos, stellar cannibalism, and cosmic clocks, we are left not just with a collection of fascinating facts, but with a fundamental shift in perspective. Septuple star systems are more than astronomical oddities. They are philosophical statements written in starlight. They force us to confront a humbling truth: our galaxy, and by extension our universe, possesses a creative capacity that far exceeds the limits of our imagination, which has been shaped by the quiet normality of our own solitary sun. For centuries, our understanding of a solar system was built upon a single, powerful example, our own. We naturally assumed that this model, a central star with a family of planets, was the standard, perhaps even the ideal, template for cosmic architecture. We searched for other Earths orbiting other suns like our own, using our local neighborhood as the blueprint for the entire cosmos. But the existence of stable systems with 7 stars shatters that Earth-centric or even sun-centric viewpoint. They reveal that our peaceful, predictable celestial arrangement is not the rule. It might well be the exception. The universe is not a place of minimalist design, but one of extravagant, even baroque complexity. It suggests that nature's preference is not for simplicity, but for rich, dynamic, and intricate relationships wherever the physical conditions allow. Our solitary sun is not the archetype, it is simply one possible outcome in a vast spectrum of gravitational possibilities. This realization challenges the very definitions we use to organize the cosmos. What truly constitutes a solar system? Is it defined by the number of stars or by the potential for planets? Our explorations have shown that even in the most gravitationally hostile environments, pockets of stability can arise, potentially giving birth to worlds with skies filled with multiple suns. This forces us to expand our concept of a solar system from a simple hierarchy to a complex network, from a single point of light to a multi-node gravitational web. The septuple system defies our need for neat categorization, existing in a category of its own and forcing our language and our models to evolve to accommodate its reality. It teaches us that the universe does not adhere to our human-made boxes. It simply is in all its diverse and bewildering glory. Ultimately, the greatest lesson these stellar families impart is one of cosmic humility and boundless wonder. They are a testament to the power of physical laws, gravity, thermodynamics, nuclear physics, to generate structures of breathtaking beauty and complexity from the simple act of a cloud of gas collapsing under its own weight. They show us that given the right ingredients and enough time, the universe will inevitably produce arrangements that seem, to our limited minds, impossibly improbable. The existence of a septuple system is a declaration that the cosmos is far stranger, more dynamic, and more creatively fertile than we ever dreamed. It stands as a permanent invitation to keep looking upward with curiosity, to keep questioning our assumptions, and to remain open to the next great discovery that will, once again, redefine our place in the grand tapestry of existence. We have journeyed together through 50 of the strangest discoveries about these gravitational marvels, from their turbulent births in ultra-dense stellar nurseries to their potential futures as factories for gravitational waves and cosmic gold. We have seen how their intricate hierarchies provide a framework for stability amidst chaos, how they warp time and space, alter stellar life cycles, and create skies of unimaginable complexity. This exploration reveals a universe that is not merely vast but infinitely creative, a place where the rules of physics can orchestrate arrangements so complex they challenge the very definitions we use to understand the cosmos. Our own solitary solar system, once the model for what we considered normal, now appears as just one quiet possibility in a spectrum of celestial architectures that includes families of 7 suns bound in an eternal, dynamic dance. The true legacy of studying these systems is the profound shift in perspective they demand. They are a powerful reminder that the universe operates on a scale of both grandeur and intricacy that can humble even our most ambitious imaginations. The existence of such stable complexity forces us to reconsider our place in the cosmos not as inhabitants of a standard model, but as witnesses to a reality where extravagance is a fundamental principle of creation. Every new observation, every flicker of light decoded from a system like our Cassiopeiae, chips away at our assumptions and opens new chapters in our understanding of gravity, star formation, and the very nature of matter itself. As this field of study accelerates with missions like Gaia and the relentless dedication of astronomers both professional and amateur, we stand on the threshold of even greater revelations. The coming years will undoubtedly unveil more of these celestial families, each with its own unique story to tell. The questions we've explored today are merely the beginning. What new, even more exotic phenomena will we uncover? Could there be systems of even higher order waiting to be found? The pursuit of these answers is what drives the endless curiosity of science. If your mind is now buzzing with questions about these 7 sun wonders, we would love to hear them. Share your thoughts and curiosities in the comments below. If you enjoyed this journey to the frontier of astrophysics, please show your support by liking this video and subscribing to the channel for more deep dives into the deepest mysteries of space.